I think that people is getting tired. So we will keep the hour, so we will start because we have people here. Today is the third lecture from Dan. So Dan, thanks.
Yeah, hello folks. I'm going to continue talking about neutrino experiments and detectors, and now go on to talking about astrophysical neutrinos. So yesterday we were, there it works. So yesterday we were just talking about neutrinos and studying their interactions with man-made sources, but now we can look at the sources that the universe gives us. So there's a whole wide range over many scales, both of energy and flux that you're looking at here. And so two of these fluxes were incredibly important for fundamental physics for understanding how neutrinos work: solar neutrinos and atmospheric neutrinos, which collectively with SNO and SuperCam prove that neutrino oscillations exist. So that's important enough that I'll talk about that tomorrow in the oscillation lecture. But so today I'll just talk about these other fluxes. So cosmological neutrinos, what we can do to detect these really, really low energy guys over here. And also neutrinos from a core collapse supernova up here, and also these very high energy fluxes termed here from active galactic nuclei and from cosmogenic neutrinos. So those are the four fluxes that we'll talk about today, and they really do just scan the full range of neutrino energies that exist. The first is the cosmic neutrino background. So these are relics from the Big Bang, so just like the cosmic microwave background. So the photons are produced just as the universe was cooling enough so that the atoms were forming instead of just having plasma around. And plasma is very opaque to photons, but when that plasma coalesces down into atoms, the photons become free streaming. And right at that moment, about 300,000, 400,000 years after the Big Bang, the universe is cold enough to let these free streaming CMB photons go through the universe, and that is what we now see in our optical telescopes now, or in our microwave telescopes. Earlier in the universe, there was also neutrinos that were in thermal equilibrium with all the other standard model particles. And there was going to be similarly decoupling of those neutrinos from the rest of the standard model particles. But of course, it's going to happen earlier than the photons because the neutrinos are much less interacting. And we know from cosmological models that, we can actually calculate the temperature of this decoupled neutrino flux, which should be right around 2 Kelvin. It's fixed to the CMB photon temperature just by related by the number of degrees of freedom. And the kinetic energy, we can just calculate. It's 3/2 times that kT. That works out to just about 0.5 milli-electron volt. So we know from the delta m squareds in oscillations that each of the flavors of neutrinos will have a effective mass higher than that 0.5 MeV. So this is kind of weird. We have a flux of non-relativistic neutrinos, and we have to find a way to detect them. That way comes down to Steven Weinberg. He said, okay, let's look at a particular nucleus that's radioactive but has a low Q value. A good candidate is tritium. So tritium will decay to helium-3, an electron, and an antineutrino. And then we can just compare that to the process where we stick the antineutrino over on this side. We have a neutrino hitting a tritium atom, and then we make helium-3 an electron. So there, in the second process, you just have a little bit more oomph from the neutrino on the left-hand side of the equation to give you a little bit more energetic electrons in your detector. And you can just look at the kinetic energy maximum for the electron, which is basically just the differences of masses here. And here we have the neutrino mass comes in with a negative on the top and a positive in the bottom, along with some little kinetic energy. So the endpoints for the electrons in these two cases is going to be different by this factor of 2 times the neutrino mass plus whatever kinetic energy the neutrinos have. But the neutrinos are non-relativistic, so this is basically just an asymmetry of 2 times the neutrino mass. So since we're talking about the neutrino mass as being sort of the main signal in doing this experiment, you know that it's going to be incredibly challenging. It's not exactly proven right now that we can do it, but we have one very good idea that looks incredibly promising. And you need to, it's basically a 3-step process, and you need to have very good control of your experiment in each of these 3 processes. So the first is making sure that your tritium is incredibly cold. So tritium is it's an isotope of hydrogen, so it likes to form, it likes to bond with hydrogen itself, it likes to be in a molecule, but that molecule will have some sort of vibrational energy in it, and that vibrational energy is enough to kill, that energy is greater than 2 times the neutrino mass, so that's enough to kill your sensitivity to the cosmic neutrino background. So you have to basically find a way to have atomic tritium instead of molecular tritium and cool it to very, very low temperatures. And they do that with molecular traps, with atomic traps. And then the next step here is an electromagnetic filter. They have something a lot more fancy, but the basic idea here is, okay, so we have the Q value of tritium is 18,592 electron volts. So let's just put a potential difference here of, that Q value -1. That means if you have the most energetic electron coming through here, it's going to lose energy in this electromagnetic field and come out this side with 1 electron volt of kinetic energy. They have a more complicated electromagnetic filter to increase their efficiency, but in essence, that's exactly what it's doing. And then the last step here is, well, you have a 1 eV kinetic energy electron. Well, let's just measure calorimetrically measure the kinetic energy that has. Let's have a little bolometer, a heat sensor that measures that kinetic energy down to 5% energy resolution or better. So basically with final goal energy resolution of 50 MeV. This is their current target, and it should be achievable if you have this 3-step process and these all go well. And this is sort of what the experiment will look like if successful. So this black line here, that is the true tritium endpoint. And then let's just make some assumption for what the lightest neutrino mass is. Let's say it's 50 millielectron volts. And we'll have an energy resolution, well, let's say it's 10 millielectron volts, so better than their benchmark target, but so this is sort of an optimistic scenario. So yeah, here's the tritium endpoint. So the beta decays will be, suppressed by, they'll be shifted down by 1 neutrino mass, and then the C nu B events will be shifted up by 1 times the neutrino mass. And so you see a difference between these two distributions here of 2 times the neutrino mass. And since this delta, this energy resolution is smaller than the lightest neutrino mass, you can resolve these two distributions reasonably well. You can, unequivocally say that these guys over here were all interactions, were all actual decays of the tritium, and these were all C nu B neutrino captures on the tritium. Yeah, so right now, this is a little bit of an optimistic scenario, but even if their performance looks a little bit worse, they can still see handfuls of events of C nu B interactions per year. Right now, they're still really prototyping whether this 3-step process will work, but it looks promising. We should understand by about 2030 whether this will actually work, and maybe in about 10 years have some data and actually have discovered the C nu B. Some evidence of the Big Bang from 1 second after the Big Bang. So that would be fantastic. Yep. Yeah, so the double peak here basically comes down to the fact that there are multiple neutrino flavors. And if you look at a neutrino flavor, its effective mass is going to be some sum of PMNS matrix elements times the mass of the mass eigenstates. And so if you look at different flavors, they're going to have different values for that. And so that's going to give you sort of this double peak structure. Right, so sort of nu e's over here and nu mu and nu tau.
Nu mu and nu tau will interact the same way?
I mean, of course, they will have oscillated. They'll really come as mass eigenstates into your detector, and so there will be sort of a sum of the 3, and you'll only select, a portion of that flux.
Okay.
Right. Yep. Okay. Yeah. So thanks. Going on to supernova neutrinos. Yeah. So if you think about neutrinos, they are usually thought of as just incredibly weakly interacting. But they're actually responsible for some of the most explosive, some of the most violent explosions in the universe. That is the explosion of core collapse supernova. And yeah, so during the collapse here, the matter becomes incredibly hot, sort of on the scales of tens of MeVs. And the star will want to, this core that becomes a protoneutron star will want to cool as fast as it can. There's a bunch of matter out here surrounding the protoneutron star, so obviously you can't have electromagnetic radiation taking away any of that energy. The only way you have to cool is by releasing neutrinos. So you release something like 10 to the 57 neutrinos with an average energy of about 10 MeV in about 10 seconds. And that 10 to the 57 10 to the 57 neutrinos released over that 10 seconds is enough to basically impart some momentum to the outer shells of the gases of the star to actually give them some momentum and explode it outwards. So that is the neutrinos propelling the explosion. So yeah, let's look at the phases of a supernova explosion. They basically come in three. There's the neutronization burst, accretion, and cooling. So neutronization burst, that is fundamental particle interaction. That is you have in the protoneutron star, early in the star's life, when it's a healthy, happy star, there's going to be some equilibrium between pressure produced by fusion pushing the star out and just gravity trying to collapse the star back in. But as the star runs out of fuel, the fusion pressure goes down and down, so the core just sort of shrinks in on itself and becomes more and more dense. At a certain point, you are buttressing up against the Pauli exclusion principle. You just can't push the electrons down anymore. And so in this neutronization burst, you say, okay, we don't have enough fusion pressure to support our weight under gravity, so we have to get rid of these electrons because we don't like the degeneracy pressure that they're placing on us from the Pauli exclusion principle. So the protons will eat up these electrons and make a neutron and an electron neutrino. So this neutronization burst gives you this prompt flash of a bright flash of electron neutrinos, just the electron neutrinos flavor, which is this black curve. After that, the core of the central core that was sort of in this degenerate electron state collapses down into an incredibly dense protoneutron star. So the gases just on the outside of that protoneutron star are going to collapse in and sort of bounce off of that protoneutron star. That basically forms a shock wave from the bounce expanding out into the stellar interior. So that shock wave is really what to think about when thinking about this collapse mechanism. So the shock wave will make it out a certain degree out from the center of the star. We say that it stalls, but neutrinos produced by accretion of matter onto that shock wave is going to produce a neutrino flux enough to impart some momentum on that shock wave and get it to expand outwards. So during that accretion phase, we have this infall of matter producing neutrinos of all flavors, which are pushing this shock wave out eventually. And when the shock wave actually does start expanding, then the density lowers and the protoneutron star basically starts cooling here over a couple hundred milliseconds. So there's really a qualitative difference here. The neutronization burst gives you just a flux of electron neutrinos, but here in the later accretion and cooling stages, you have fluxes in thermal equilibrium of all different flavors at similar energies. After that 10-second or so process has happened, after you've gotten rid of 10 MeV scale neutrinos, you still have a neutron star that's not quite stable. So a neutron star that is stable is some degenerate Fermi gas. But here in the aftermath of the explosion, you have a lot of neutrons above the Fermi energy, so they're rattling around with too much kinetic energy. So they still have to find a way to cool themselves that way with some sort of lower energy nuclear process. And that comes down to these ERCA processes. Something like neutron decays gives you an antineutrino and a proton and electron. These proton and electrons will go flying off and combine with other protons and electrons and give you a neutron and an electron. And the process just continues until you reach this degenerate state. And this leads to neutrino emissions with temperatures less than 10 MeV at timescales much longer than 10 seconds. And it is called the ERCA process, named after the neighborhood of Rio, which is why we had the picture on the title slide. And it's explicitly named after the casino in ERCA. So this is where basically George Gamow got the idea. And he said that he really liked this name because the Urca process results in a rapid disappearance of thermal energy from the interior star, similar to the rapid disappearance of money from the pockets of the gamblers of the Casino de Urca. So this is one of the better named processes that we'll see in particle physics. Humans are an incredibly lucky species. So, we just started to have detectors that could see neutrinos from a supernova in around the early 1980s. And then basically 5 years or so after Kamiokande 2 came online, we got this observation of this star in the Large Magellanic Cloud, which gave us a sharp pulse of neutrinos. And we detected about 22 in 20 or so seconds. This is looking at the various detectors that recorded them. So the red is Kamiokande 2 interactions, blue IMB, Irvine, Michigan, Brookhaven. So these are both water Cherenkov detectors. And then the green points here are a scintillator detector, Baksan, which is in the Caucasus Mountains of Russia. So this was a fantastic discovery. So people incredibly happy that we discovered this new astrophysical phenomenon. And coming out of this early detection of supernova neutrinos, there was both a lot of interest in detecting this in the future with bigger detectors, and this became sort of a motivating reason to build larger and more sensitive detectors. But there's also just countless papers that were based on these 22 events, everything from like nuclear physics and astrophysics up to like very fundamental particle physics questions like axions and neutrino-neutrino interactions. So just phenomenal amount of information that can come out of supernova neutrinos. It's just such an exotic medium where you have neutrinos so dense that you actually get neutrino-neutrino scattering. So like nothing else in the world, so why not use this as a laboratory for fundamental physics? Yeah.
This might be a naive question. So this whole flux of neutrinos happens at just like 1 second, and we were just lucky enough to be looking at the right time, at the right thing?
Well, these detectors are always looking for events, right? One of the main goals was to actually record solar neutrinos. So you don't know when solar neutrinos are coming, so you just have to have your detector always sensitive. But then the thing that tipped us off that the supernova came is, well, usually we might expect one event per 10 seconds. Now all of a sudden we see 10 in 1 second. And so, the fact that we see such a pulse nature means that something was going on. We look at it and we see this in three different detectors. We see the light signal a couple days later, and so, now we know that we do actually see this star blowing up. That's what these guys are.
And the light signal were like the telescopes looking at this supernova region?
Yeah, exactly. So after we saw this, it was actually a telescope in Australia that pointed to the Large Magellanic Cloud and saw a new star, a new supernova as bright as that galaxy. Yep, perfect. Thank you. So a little bit of reminder from yesterday, what we talked about for the dominant interaction channels in this sort of 10 MeV neutrino energy region. So if you look at water and scintillator detectors, so water like the Kamiokande 2 detector or Super K now, so chemically there's just a lot of free protons here. That's basically H2O or CH2 for scintillator. That means that we're going to get inverse beta decays. So these anti-neutrinos, the anti-electron neutrinos are going to capture on protons, give you a positron here, which gives you some prompt energy, and a neutron here, which rattles around in your detector until it captures and gives you some delayed energy from gamma cascades. And so there you have that correlated signal, so you can hopefully reject your background quite efficiently. And then if you go look at liquid argon TPCs, the argon gives you a very high neutrino nucleus cross-section. So you basically have the neutrino absorbed in an argon atom, spit out an electron and a few de-excitation gammas. There's no timing differences here generally. Everything is prompt, but you in a TPC can get good tracking information. So you can, for instance, see an electron track here along with some blips from de-excitation gammas. And so again, you can use this distinctive topology to separate out the signal from your background events. And the last is sevens, which we talked about yesterday. So these low threshold dark matter detectors are going to be able to see tens of keV nuclear recoils produced by supernova neutrinos. And this is just a standard sevens process. You'll see a little bit of kinetic energy acquired by the nucleus. And this is, a really interesting process because it is flavor blind. It tells you something about the total flux of neutrinos from the supernova rather than just the anti-electron neutrino flux or the electron neutrino flux like you get in water scintillator and argon, respectively. And yeah, so this is just a statement there. There are fundamental differences in these detection media that give you access to different parts of the supernova, all of which we want to understand separately, and we want to build up this global understanding of the neutrino flux by putting this technology together. So that's what we are looking at here. So really, our goal as experimentalists is to understand the triple differential neutrino flux that's coming out. So that's the three variables there are time. So this is time since that bounce happens, and the energy of the neutrinos that are coming out. And then each of these colors are flavor, the NUI bar, and mu bar, nu tau bar, which we can't tell the difference between because the neutrinos are too low energy for charge currents. So we just collectively call these nu x. And so really the goal of us as supernova neutrino physicists is to build a diverse program that is sensitive to all of these flavors separately. So you build multiple detectors with different detection schemes and different strengths. And so that's what this table is looking at here. So for instance, if you build DUNE, liquid argon TPC, it's going to almost entirely see electron neutrinos. Build a bunch of dark matter experiments. They're searching for other physics there, but when supernova neutrino burst comes along, they will see a burst of sevens from a supernova, which gives you nu x information. And water and scintillator give you basically a good understanding of what the NUI bar flux is. So putting together these four types of detectors, we can succeed in our goals of measuring all the flavors and the time and calorimetric energy of neutrinos that are coming out. Yeah, so upcoming supernova detectors. So we live in a pretty exciting decade. So in the 2020s, we will have updated, we will either have completed, we have now either completed building some of the detectors with these different detection strategies, or we'll have new ones coming online in the end of the decade. So the first here is water Cherenkov. We talked a lot about Super K that's been running since 1996. It's well established, but it will be upgraded to Hyper-Kamiokande with 260 kilotons of fiducial volume compared to Super K's 22.5. And so these are approximately to scale, as well as I could do in PowerPoint. And going up to Hyper-K just means that you'll get just a boatload of statistics. You'll get something like 50,000 events from the next core collapse supernova that happens in our galaxy. If we go to scintillator, this is coming up to the new detectors. So this is going to be a giant organic liquid scintillator detector, so 20 kilotons of liquid scintillator target. That is held in this acrylic balloon here. Outside here you have basically mineral oil with no scintillator in it, so you don't get any light in this border region. But in your fiducial volume here, you get an enormous amount of light, which can make it through this acrylic sphere and be measured in your photodetectors. They have absolutely phenomenal photodetector coverage here. There's 78%, and that is split in between these two sizes of detectors. So there's 20-inch PMTs and 3-inch PMTs in the middle here. So any ideas why they have these two different sizes of PMTs in their detector? That's a very good guess. There's an experiment Theia that tries to do something like that, but that's not actually what they're doing here. It's actually dynamic range. So scintillator just releases boatloads of photons. So even like 50 MeV or so, neutrinos will start saturating these big PMTs. So if you want to study something like atmospheric neutrinos, which have GeVs of energy, you need smaller PMTs, which, just because they have a much smaller area, they'll collect fewer photons and will saturate at much higher energy scales. So, using these two different types of photodetectors allows the detector to expand its dynamic range. Yeah, so Juno is really exciting right now. Its construction is going phenomenally. It will probably turn on by the end of the year. And if we look at its sensitivity to typical galactic core collapse, something like a couple of thousand events that you'd expect. So the next is argon. So I am a member of DUNE, specifically looking at solar and supernova neutrinos. So this is sort of my bread and butter along with coherent. And so Dune is building just absolutely giant liquid argon TPCs deep underground in the Sanford Underground Research Facility. So here we have a cavern that's already excavated to put 4 17 kiloton TPCs down there under a huge overburden, something like 3,300 meters of water equivalent. And again, you'll see something like a few thousand events from a typical core collapse. And just a little bit more about what the Dune detectors look like, because this is what I do in my day job. These are going to be basically the almost about half the size of a football field, so 62 meters long, 13 meters tall. The charge is going to drift vertically, so from the central cathode to anodes both on top and bottom. So there will be wires on the top and bottom to collect charge from supernova events. And then these light teal on the blue on the dark blue plane. These are basically photodetector units to see the scintillation signal in the argon. And there are also some photodetectors here along the walls, which you can't see so well on the PowerPoint, but they will be there. Right, and I also do want to talk about the photodetector system, since it was designed just up the road in Sao Paulo State, up in Unicamp. As a charged particle tracks through argon, it's going to release some scintillation. But since Dune is such a giant detector, we don't want to just plaster the entire surface wall, area with, say, PMTs. So we have a smarter way of doing this. We basically have a light trap, which takes the very low wavelength, 127 nanometer light wavelength, shifts it to something that is visible in the to PMTs, and in doing so, you change the index of refraction of this glass structure here, and basically you get total internal reflection of any light that enters within this waveguide. And so you get light that comes in and just bounces around until it can finally get captured on a light detector. And so this is again, they're fixed to the side of the anode here in one of the Dune FAR detectors, like so. And this is a way of basically increasing your photodetector coverage without having to spend a lot of money on photodetectors themselves. So this is just an economical way of doing your physics quite well. Yeah, and then we also have dark matter. So I think for time, I'll just refer you to Javier's talk from yesterday. But there's this flux in the neutrino fog coming from diffuse supernova from very, very far away. That raises by about 8 to 10 orders of magnitude and gives you a signal right around here. And so you'll see this bliss of something like hundreds of sevens events coming into your liquid noble detectors, primarily your xenon and your argon detectors. And you'll get, if you integrate all those up together, you'll get sort of on the order of 1,000 sevens events that you can tag from the typical core collapse. So yeah, now what can we do with physics? So the neutrinos are going to escape from the collapsing star before any of the light signal does. The light signal only leaves when that shock expands to the surface of the star. The neutrinos get out on the order of seconds, so much faster. So we can actually basically be an early warning system for optical astronomers to basically figure out where we think the supernova neutrino flux was coming from, and tell the optical astronomers, point back to that source location so that you can see the shock breakout. So water Cherenkov detectors and argon detectors can both do this very well. This is a plot from Super Kamiokanda. So all of the little green and blue boxes that you see here are individual reconstructed events. So the green is the dominant channel, the inverse beta decay, but the blue is this small subdominant channel of neutrino electron scatters. So that's what you're seeing in electron here. So an electron neutrino comes straight from the supernova, scatters off of an electron, and since the electron is light, the electron and neutrino directions are fairly parallel. So you basically get an electron coming and that is reconstructed in the direction opposite from the supernova. So you can basically look at the distribution of electron scatters that you see, sort of pick about the middle, say that is the direction that the neutrinos were going, so point back and say, optical astronomers go point there. And for the typical galactic supernova, you can get something like 1 to 5 degree resolution. So we can limit the sky from 40,000 square degrees to a few square degrees. So very incredibly helpful for that. Yep.
What's the delay between the neutrino and the light signal from
Yeah,
the supernovas?
Can be anywhere from seconds to days. It depends a lot on like the specifics of the progenitor, which can be, if you look at a blue supergiant, they're actually sort of the size of the sun, or you could have a red supergiant, which is, this goes out to Earth's orbit. So just that, factor of 100 or so difference that the shock wave has to propagate means that the delay can vary by a factor of 100 or so.
And do you know by looking at the neutrino signal how big the event was?
To some degree, if you can, it's complicated. So there's just a lot of uncertainty on, how many neutrinos are produced. So there are fundamental astrophysical uncertainties that get in the way there. So one of the reasons that you want to measure this burst is so that you can, help calibrate that, so that you can understand that physics. Yep.
Thank you.
Yeah, but definitely the right questions to be asking. So we have really these 4 detection schemes. So I want to go through and one by one talk about, why each one is valuable on its own. So one thing, let's start with scintillators. And so what Juno has going for is it just has phenomenal photodetector, fantastic light yields. So if you look at the plot that you're seeing here, this is basically the Hertzsprung-Russell diagram for neutrinos. So here on the x-axis, you have an inverted scale of temperature, so lower temperature stars over here. And the y-axis, this is just the luminosity in neutrinos relative to the sun. And these blue and purple traces here, these are the very massive stars. So this is the life cycle of stars that will go supernova and give you neutrinos. If you look at just the very end stages of the star, even before you get to a collapse here, you get things like silicon burning, where you have not quite the flux that you would get at a core collapse supernova, but possibly large enough to see from a detector on Earth. And since scintillator has very good light yield and has very low threshold, you can potentially look for these neutrinos, which ultimately come from silicon burning into iron. And this is sort of the expectation of what Juno will be able to do. So this is basically for the closest candidate star, Betelgeuse, going off. And here you have expectations for inverse beta decay, what sort of visible energy that you'll see in your detector, and neutrino electron scattering. With a threshold of about 0.2 MeV, Juno expects that they can see these pre-supernova neutrinos for collapses that happen out to about 1.6 kiloparsecs. So that's about 1/6 of the distance between here and the center of the galaxy. So the coverage isn't that great, but if you can actually see these pre-supernova neutrinos, that's sort of like an early warning to the early warning experiments. You can tell sort of in the hours before the neutrino burst actually happens, experiments like Super K and Dune better be up and running because the neutrino burst is about to come. And this bottom left, right plot is exactly just the number of inverse beta decay and electron scatters that you'd expect as a function from time before collapse. So you see this sort of steady ramp up to thousands of neutrinos per hour just from fusion from these stars outside the solar system. Yeah, and one of the simplest questions that you can ask is, just how many neutrinos are produced in the core collapse. This is where dark matter experiments really excel. They are sensitive to all the flavors, so there are no oscillation uncertainties. So if you look at this plot as a function of time, this really just tells you how many neutrinos are produced as a function of seconds since the bounce. And yeah, the blue here is the distribution of expected neutrinos as a function of time for xenon n-ton, the Lux Zeppelin experiment, or Panda X4 ton. So those are the 3 experiments that are running right now in xenon, and we'll collectively sort of each see about 100 events for a supernova. This plot here is looking, basically showing what the backgrounds will look like in a burst. Since these neutrinos all come at once, the backgrounds are basically unimportant since you're integrating over just such a small time frame. And so you see the signal is very, very clearly observed over internal argon-39 backgrounds and backgrounds from just single electron deposits in the detector. So this will be a very clean signal, both in terms of backgrounds, and will tell you a lot about the physics in terms of just the raw luminosity. So why Dune is really important. So Dune is sensitive to the electron neutrino flavor, and that is also the flavor that gets spit out during the neutronization burst. So if you look at this, this is neutrino events in Dune as a function of time. If you look at a water Cherenkov detector or a scintillator detector, it will really just roll on here and in the accretion phase. And so you really need to build an argon detector, something that is sensitive to electron neutrinos, to study this neutronization burst. And neutronization bursts are often considered sort of a standard candle. We expect that these will happen in every single core collapse, and we basically understand what luminosity of neutrinos come out. It's basically something you can work out from the back of the envelope. You have some massive neutron star that has to deleptonize. So every time you have a proton and electron going into one of those neutrons in the final neutron star, you basically have to have one NUI candidate that contributes to this peak here. And so this is a really great way to study, new neutrino properties, magnetic moments, neutrino scattering in detectors like DUNE. So why you want to build a water Cherenkov detectors? So first, they're just absolutely massive. So you can look for, small structures within the supernova mechanism. And one thing that you can do here is look for Sassi oscillation. So standing accretion shock instability. So you have this shock wave out here, which sort of stalls in the early collapse. And it has to basically get some momentum transfer from the neutrino burst to expand outwards. But when it's sort of just stalled, it can contract a little, and because of a lower neutrino flux, which will then heat the star and make more neutrino production actually happen, and then expand the core outwards. So you get this sort of oscillation in the radius of the shock, which turns into oscillations in the sort of mean energy and the rate of neutrinos that are coming out of the star. And so if you have a large enough detector, you can actually detect these wiggles, measure the frequency of these wiggles, which tells you something about the actual physical properties of the nuclear medium in which this oscillation is happening. Just a final word here. This is very much a global picture. No experiment can handle supernova neutrinos on their own, so we are very much a community and we talk to each other. One important aspect of that is this news network. Since these supernova bursts are rare, they happen a couple times a century, we absolutely want to collect all the data that we can. So we have all these detectors that are collectively talking to each other. And if one sees a signal that looks incredibly like a supernova burst, it will disperse an alert to all these other detectors, and they will continue to record the data that in a coincident time region. And you can also get alerts from SNOOS yourself, so just sign up for the email list. If you have iPhone, there's also an app for that. I have Android, so I'm always a little bit bitter that I can't get that myself. But yeah, this is an important aspect of fostering a successful and collaborative community in the supernova detection field. I want to say one last thing about supernova neutrinos. So usually we think about supernova neutrinos coming as a burst from an explosion that happened in the galaxy. But of course there are supernova everywhere in the cosmos, and so you can actually think about that giving you some sort of signal in your detector. So basically the neutrino flux as you go farther and farther away goes like 1 over r squared, but the rate of supernova goes like r squared. So those sort of cancel out. So if the universe was static and infinitely long-lived, this flux would basically integrate up to something infinite. It would diverge. But luckily, the universe is only finitely old, and there's also redshifting at high z. So that's going to give you some finite flux as a function of energy coming from the so-called diffuse supernova neutrino background. And you can write it down as just an integral over, say, the rate of supernova as a function of redshift times the typical spectrum for supernova and neutrinos that you see, plus this additional factor which accounts for lowering the density far away from us as inflation is throwing the universe apart. And if you do this, you see that you get a low flux, something like 3 neutrinos per square centimeter per second. That's compared to a few times 10 to the 10 for solar neutrinos. So this is a very tiny thing that we're looking for. But of course, experiments can go ahead and do a search for this. So Super K right now is the most sensitive detector. It's a water Cherenkov detector, so it will be doing an inverse beta decay search. So yeah, we see an electron coming from prompt electron coming from these DSMB interactions. But if you just have a water detector, the neutron is going to capture on basically a free proton on hydrogen 1. That, if you look in the table here, that gives you a Q value, a 2.2 MeV gamma that comes out from that capture rate interaction. Unfortunately, that's below the threshold for Super K. The Super K threshold is 3.5 MeV. So right now, Super K can't exploit the very fantastic prompt and delayed coincidence of energy here, and so they can't really reduce their backgrounds. And you see that exactly here. This plot is from a phenomenological study looking at DSNB expected signal along with intrinsic electron charge current interactions, and this pesky green distribution, which comes from not neutrinos, but basically muon neutrinos that produce a muon below threshold, so you can't see the muon, but you do see the decay electron. So this is basically a Michel electron that does not produce a neutron that's giving you some sort of background. So if you were to instead have a lot of hydrogen in your detector to capture neutrons, if you were to put an element like gadolinium in your detector, which has a much higher Q value, all of a sudden you can exploit this prompt delayed coincidence and kill this green background. And so that's exactly what they did. So I mentioned the gadolinium upgrade for Super-K. It's basically exactly for this measurement so that you can reduce all that atmosphere, that Michel, that muon decay background. And now we can look at this plot down here. This is the reconstructed total energy from gamma cascades. So here you have captures on gadolinium, neutron captures on gadolinium, plus all just sort of accidental backgrounds here. These are very clearly distinguishable. And so we can put a cut and see exactly this delayed energy after prompt energy deposit in a DSNB event. And it looks like with just results that were released a month ago at Neutrino 2024, we do actually have a tiny little hint that we are seeing some supernova neutrinos here. So this is looking at about 3 years of running with Super-K gadolinium and something like 25 years running with Super-K without gadolinium. And it turns out that those two time periods have roughly the same sensitivity. So, you know, we accumulate statistical sensitivity to the DSNB about 10 times faster now with the gadolinium upgrade. And this is looking at their data spectrum here. So this yellow distribution, when you have gadolinium, is your dominant background. These are the atmospheric neutrinos. And then this red hash distribution is your best fit to the DSNB. You see a few excess events here, right where the bulk of your DSNB events are. So, well, this is only a 2.3 sigma signal, so we do really have to sit here and wait to bolster more to get more statistics. But it does look like we're seeing a DSNB flux of, you know, a couple per square centimeter per second. So this is really exciting. We probably saw, you know, a handful of neutrinos coming from supernova that have been traveling for 1 billion or so years, coming from gigaparsec timescales to interact in Super-K and give you these few events. Right, so that is it for supernova neutrinos. So now I want to switch gears and talk about the ultra high energy neutrinos. So these are large, you know, cubic kilometer observatories that we have, like IceCube pictured here. And yeah, so just an idea of the landscape. You have, you want to build just giant water Cherenkov detectors. You have two options. You can build them either in glaciers or in the ocean. So the glacier technology, this is really IceCube right now. And I talked about this a little on the first day, but basically you have these long strings of photodetector units instrumented in this bottom kilometer or so of the detector. The surface area of the IceCube detector is also about a square kilometer, so in all it gives you a cubic kilometer or a gigaton of mass. It's right here, right at the South Pole. And you don't have, you can't do particle identification by looking at, you know, fuzziness of rings like you can in Super-K, but you do see differences between tracks like you would get from a muon and, you know, big bulbousy showers like you get from an electron or tau neutrino. So yeah, that is the, you know, that is the IceCube detector, the IceCube strategy. You can also just sink these lines of photodetectors into the open ocean. So this is what KM3Net ARCA does. This is one of their photodetector units, which is sort of an upgrade from IceCube. So you have multiple photodetectors pointing in different directions, so that gives you better light collection. And so you also, so you have KM3Net ARCA, which is off the coast of Sicily. And then you also have a similarly sized, you know, cubic kilometer telescope in Lake Baikal in Russia. And both of these detectors are currently undergoing construction, so a portion of the detector has been built, but it is still being expanded. And if you look at these two different strategies, there are advantages of each. So in ICE, you actually have a better transmission of the Cherenkov light, so you can build your photodetectors further away. That basically means that you can get more mass for the same amount of money. If you look at the detectors in liquid water in the ocean, there's actually less optical scattering of photons in liquid water than in ice. And so that means that the trunk of light that you measure is bouncing around less, so there's less, your angular resolution becomes better because there are fewer detector smearing effects in the liquid water. So, these liquid water detectors are going to be much better for pointing back to local sources. So one thing that you can do is just, ask, is the Earth transparent? Of course, at MeV scale energies, we talked about needing light years of material to stop neutrinos, but it turns out that the Earth will eventually stop these high energy neutrinos. So basically say that the cross section, if the cross section is greater than 1 over the number density times the length, then these neutrinos will get captured in Earth. And if you plug in the numbers, that means that basically for cross sections greater than 3 times 10 to the minus 34 square centimeters, the neutrinos are actually going to get filtered by the material of the Earth. If you look at the cross section for interaction, that's sort of this magic regime where the Earth starts to become opaque is sort of right in the middle of IceCube's region of interest. So this is about 200 TeV here, where the Earth actually becomes opaque. And this is a study by IceCube exactly looking at the color here is the transmission probability as a function of neutrino energy and the zenith angle. So here at about 200 TeV, you see exactly that you get pretty poor transparency of the Earth for angles more than about 130 or so. So this basically means that you're going to limit the amount of sky that you can look for. You can't look for neutrinos that are coming from straight up because you have a lot of atmospheric muons which can give you backgrounds. So you need to look for those that are coming upwards from neutrinos that happened on the other side of the world. But really, you're only going to get a small portion of the possible 4-pi coverage in each detector. And so that is the motivation why you have multiple detectors across the world. So we have IceCube down here, CAM3net, ARCA here in Sicily, and then Baikal up here in Lake Baikal. There are also a couple in the Sea of Japan here that are coming underway. And then there's also the P1 detector off of Vancouver Island in Canada. And if you look at the complementarity here, much like the supernova channel, supernova physics, you want to have as many different detectors with different detection media. Here you want to have as many detectors on different parts of the world so that you can really cover the full sky. Right now, these are sort of, this is of course energy dependent how much of the sky you can cover, but right now, sort of for the typical astrophysical neutrinos, this is what could be probed with these 3 detectors. So another region where complementarity happens very well. So yeah, the next goal here for Super K is, okay, we have detectors that can measure these very high energy neutrinos. So let's measure these astrophysical neutrinos. Let's go outside the solar system, outside this pesky atmospheric neutrino background, and start to measure this pink distribution. So yeah, the first step there will just be, measure it, look calorimetrically at the neutrinos that you have, and separate the atmospheric and the astrophysical neutrinos. And the second step will be, classify those neutrinos that you see. So let's just discover these neutrinos first. So this left plot here is from IceCube. So the colored stacked histograms here, these are atmospheric neutrinos that are being recorded in the detector. And then this red line here are those astrophysical neutrinos, those neutrinos from the pink flux line on this plot. And so you can clearly see that above about 10 to 100 or so TeV, the astrophysical neutrinos start winning out over the atmospherics. And so you see sort of this knee in the distribution, and you can understand what the total flux of astrophysical neutrinos is just by measuring the normalization of this red curve. And IceCube was able to do this in pretty early on, which means that the water trunk of detectors, so Baikal up here and CAM3net ARCA down here, can already do similar things with limited exposure from partial detectors. So you can already see that you're getting some evidence of the astrophysical neutrinos up here and over here. The next thing that you want to do is understand where these are coming from. So this is IceCube's recent results showing that there is an excess of TeV to PeV scale neutrinos coming from the Milky Way. So we have an image of the Milky Way here in optical and different wavelength bands of the electromagnetic spectrum. But now we actually do see that there are sources of these very high energy neutrinos coming from the galaxy. And we can see them as these sort of hotspots in the neutrino flux coming from IceCube. If we expand this to the full sky map, this is exactly what it looks like. So this black line here, that's going to be the equatorial plane of the galaxy. All these little stars and triangles and boxes, these are sources that we might expect might be spitting out TeV to PeV scale neutrinos. They're mostly supernova remnants and related nebulae. And we see that we do see a lot of this heat map sort of correlated along some of those stars. So we're really just at the birth of this neutrino astronomy field, but eventually, when more detectors come online, especially the water trunk of detectors with better energy resolution, we can maybe start to look at this excess neutrino flux and correlate these to specific galaxies, different objects within our galaxy. So this is something that in the next decade we will have a lot more information on and be able to say something about the astrophysics. So the next thing that you want to do is, reach out not beyond our own solar system, but beyond the whole galaxy, and start to look for sources just beyond the Milky Way that might be giving you some of these high-energy neutrinos. The first one was a 4-sigma identification of multi-TeV neutrinos coming from this particular galaxy here. So this is what it looks like in the optical. So this is a galaxy with a very hot active galactic nucleus. So this is a supermassive black hole, which is just emitting all sorts of radiation in all the bands, and we now know that also includes the neutrino band. This is a so-called SAIFR galaxy, which is the galaxies that have this sort of structure with the active galactic nucleus. And if you repeat this structure, looking for other SAIFR galaxies that we know, we see that there's sort of a similar neutrino spectra with sort of 2 to 3 sigma evidence for some sort of excess coming from these guys. So this looks like to be a specific qualitative type of astrophysical object that produces these types of neutrinos that these telescopes can see. And now with running for longer or increasing exposure, more neutrino telescopes coming online, upgrading IceCube, we'll be able to actually make precision statements about and classify these sources. So one last thing to talk about, instead of talking about these astrophysical neutrinos, let's go up to even higher energy scales, which turn out to be neutrinos from the cosmos at large. So the typical mechanism that we have here is if you look at 10 to the 20 eV photons, they'll interact resonantly on photons from the CMB, which basically gives you a 1232 delta resonance. That resonance will decay to protons and pions. So hey, you're producing pions, those will also decay and give you neutrinos. So from these proton CMB interactions, we'll get just sort of this peak of neutrinos at the PeV to EeV scale, so absolutely gigantic energies. This is called the GZK resonance, and so I'll just refer to these as GZK resonance neutrinos. And the problem here is that they are just incredibly rare. You need to have enormous exposures to actually just see one of these GZK neutrinos. And once you actually see them in your detector, they're often bigger than your detector, so they're also incredibly difficult to reconstruct. So let's go and see how we can actually measure these guys. So basically, we really need a new technology scheme to fundamentally see these giant events. And that uses Ascarian radiation as the fundamental detection mechanism. So if you think about electromagnetic showers, it's going to produce electrons and positrons, which gain some momentum and start traveling. Usually you think about electromagnetic showers as being fueled by pair production, like over here. This is going to produce currents of both electrons and positrons. Since those have opposite charge, they sort of cancel out. But since electrons are in matter but positrons aren't, when you have a photon incident on an atom, you can Compton kick out an electron, which gives you this net negative current of negative electrons, which you don't have for the positron. So that gives you an asymmetry in the current, which ultimately gives you some sort of classic electromagnetic radiation, which you're looking at right here. So what kind of wavelengths can we search for in this electromagnetic radiation? Well, if the wavelength is small compared to the size of the event, then all these different emissions will basically interfere destructively with each other. And so wavelengths smaller than the size of an event will basically all cancel out. You won't see any coherent signal far away from the event. But if you go to radio waves, where the wavelengths are like kilometer scales are longer than the size of your events, then this emission will all add up coherently, and you see an observable signal. So basically what you want to do here is make radio telescopes for neutrino interactions. And so the first attempts to do this were with balloon-type experiments. This is the ANITA experiment. So this is, the balloon in the far distance here with a payload of a bunch of radio antenna up here. So this was also in Antarctica and was sent in flight paths along the continent. And here you're looking for, the neutrinos that are coming from upwards, but really just grazing the surface of the Antarctic continent, making some Asgardian radiation in the ice, which will then be detected by all these radio antenna. And they have a complicated analysis looking at like the polarization and the relative time delays in each of these antenna. And from that can separate out the neutrino interactions from other atmospheric or cosmic ray events. And this is sort of a look at what ANITA was able to do. So this is the data curve is this blue here. So that is what they were actually able to place on. This is the constraint that they were able to place on the flux as the flux here on the y-axis is a function of energy, and these GZK neutrinos are expected in the parameter space in this black checkered region. So this data is sort of on the level where you can make some statement about that. You're sort of just on the doorstep of the GZK neutrinos. But you need to do a little bit better, build a better, bigger detector, more sensitive detector to really get into the real parameter space. And that's really where the IceCube Gen 2 radio upgrade comes in. So I mentioned this the first day. So IceCube is trying to build a second generation observatory. The blue distribution, the blue here is, these are photodetector strings that are already included in the IceCube experiment. And that is hoped to be expanded into this orange region of optical light detectors, the standard IceCube. So basically expanding to 8 times the volume. But this will also include a massive scale of radio antenna, which are sunk into the ice. And going from an area of about 8 square kilometers to about 500 square kilometers. This is really the size to fully contain these events which are releasing Asgardian radiation. And we hope that we should be able to make some new constraint based on this giant area that we're instrumenting in the Gen 2 upgrade. And this is sort of a look at what the sensitivity will be able to accomplish. So this blue distribution here, this is expectation for the GZK. This blue distribution here, this is what IceCube Gen 2 expects to be able to do with a radio upgrade, and compared to past constraints. So this is again ANITA, this is the balloon experiment, and also notable is Auger, just the cosmic ray experiment down in Argentina. So this is a difficult measurement to make just because of the size and the low flux of these neutrinos. But in the next 10 years or so, when we might have a Gen 2 upgrade for IceCube, we will be able to make pretty precise measurements down an order of magnitude or 2 below the actual neutrino flux. So this is an exciting time to look for these high energy expansions of our understanding of these high energy neutrinos. So yeah, that wraps it up today. We've been talking about neutrinos as being incredibly feebly interacting. So in the astrophysical game, you basically flip that on the head and say, that's actually a strength for neutrinos. That means that you can actually probe into these, far away or very dense media that you can't study with other types of radiation coming out. And yeah, the neutrinos were the first fermions to decouple from the Big Bang. So we can, in principle, use neutrinos to study them, the very first second or so after the Big Bang, look at very early cosmology. But there are some R&D efforts that need to be worked out to work out the actual detection. And then we also look at the core collapse supernova. These are incredibly rare events, but they give you an absolutely enormous amount of information, both about the astrophysics of these very bizarre media, and also gives you access to a lot of fundamental particle information. And then we also have these dedicated cubic kilometer neutrino telescopes, which are looking for very high energy upward going neutrinos from astrophysical sources or from cosmology. And we're really just at the birth of neutrino astronomy in this aspect. So IceCube with 1 cubic kilometer of instrumented volume has taught us a lot. In 10 years or so, with Gen 2 upgrade, KM3net, Baikal, and Trident in the Sea of Japan, P1, we'll be able to increase the fiducial mass by a factor of about 20 or so. We might be able to make precision experiments. And yeah, these experiments here were also pretty involved in neutrino oscillations, so stay tuned for tomorrow, and we'll talk about that. So thank you. Any questions?
Thank you. So we have time for questions. Any questions? No questions? Well, remember that Martin has a question.
So both in the plots of the cosmic neutrino background and supernova neutrinos, you have shown like plots with inverse ordering and normal ordering. So the difference is just because you have like more. In one case, you have more massive neutrino, higher mass, more higher number of higher mass neutrinos than the other. It's just the effect of the mass, or.
Right. Yeah, so they're different. So supernova, this is basically the MSW effect. So the core of the supernova is high enough to, excite both the nu 2 and nu 3 states resonantly through the MSW effect. So basically, what ordering of masses matters, because what matters for the MSW effect is the nu E will be the most massive. It will come out as the most massive neutrino state, which depends which. We don't know what state that is. We don't know because of the uncertainties in the mass ordering. So for the cosmic neutrino background, what you care about is the effective mass for the electron neutrinos, which of course also depends on the mass ordering. So yeah, this is why we really care about precision measurements of oscillations, so we can remove that systematic uncertainty and get better expectations for what these signals will look like. Yep. Thank you.
Thanks. Any other question? Yeah. Otherwise, we can move
There's a couple up here.
Oh, sorry, I didn't see that.
Hey, I have a question on slide 37. You mentioned that the muons leave tracks while the electrons and tau neutrinos leave showers. How come the muons, which I think about as like the middle one, leave the different sort of signal? Like where does the difference in the signal that they leave in IceCube come from?
Yeah, so this really comes down to they're just lower energy, so there's less radiative losses. This comes down to the beta block equation. They're sort of all in the radiative regime, but if you look at the radiative losses, it just continues to rise at higher and higher energies, or higher and higher speeds. So since the electrons are at higher speeds than the muons, they'll still have more and more radiative losses, so they'll still be more and more compact. So there's still that asymmetry there.
Okay, thank you.
Yeah.
Okay, we have 2 more questions.
Hi, Dan. Thanks for the nice lecture. You showed a plot about an optimistic scenario for Ptolemy based on the lightest neutrino mass being, I think, about 500 milli-electron volts.
Yep.
How much would this get worse if the lightest one was massless? Because then you still have the mixture, so how robust would be this prediction?
If the lightest mass were completely massless?
Massless, yeah.
Yeah. So sort of the spread that you see in this distribution comes from basically the nu 2 and nu 3 states. That's the effective mass of the electron neutrinos, the sum over all the mass states. If the lightest mass was 0, then basically this would be your dominant effect. And so you'd have to basically smush this distribution right over here relative to, and similarly the tritium decay distribution would be smushed right there. So it's really just this tiny difference of 10 or so milli-electron volts, which would drive your sensitivity. That's a really pessimistic scenario. And Ptolemy hasn't actually made that plot because it's so crappy for them. But if you do look at Ptolemy, they do look at a number of reasonable potential scenarios, and you can look at the different sensitivities there. You can look up this paper, which will have that.
Thank you.
Yep.
Okay, last question.
Hi. So thanks for the lecture. And my question is related to these neutrino radio telescopes. Because I've been reading some things related to the grant proposal, and I saw that they talk mostly about detecting tau neutrinos, and I was wondering why they don't talk more about detecting electron neutrinos and muon neutrinos, if it is something related to the lepton created. I don't know if muons or electrons can create the same radio signal.
Yeah, I'm not exactly sure. I haven't read that paper. I would expect it. So at very high energies, you need the tau to decay, and you basically want to look at that, that baseline for the tau to decay. At high energy, that baseline is going to be bigger. So with this very high energy radio telescope mechanism, you can basically get a big baseline and see basically a 1-2 punch of really high energy release from both a prompt neutrino interaction and then the tau decay at a long baseline from each other. So I assume that is what they're after, and they can get a pretty clear sample of new tau interactions, but I'm sorry, I haven't actually looked at that paper, that proposal, so I can't say for sure.
Okay, but makes sense.
Yeah.
Thanks.
Okay, we thanks Dan again. We have half an hour for question later. So now we will move to the Luca lecture.
Should I do something, or maybe no? I can see it there, but not here.
Ah, okay.
Okay.
Good.
Okay, so we'll start from where we left. Finally, you will have an answer of how to search this mysterious X17 particle. I'm sure you didn't sleep last night thinking to the X17. And so we saw this interesting anomaly from the experiment Atomki, and we also saw that this can be explained with dark photon-like particles with masses of order of 17 MeV. And we also saw that there is still some available parameter space to search for this particle. It is given by the fact that this region of the parameter space produces particles that are too light for the searcher colliders, too feebly interacting to the standard model to be searched a thin target experiment, but also too short-lived to be searched at bin dumps, because they will be produced and decay within the dump itself and not be detected. So we need really some new idea to search for this particle, and what we will need really will be some very precise probe, since for this time we know what is the mass of a candidate. All the other searches that I have discussed up to now, there were no particular hint about the mass of the particle we're searching, apart the range 1 MeV, 1 GeV, which were referring for the LiDAR matter particle. And this may come from this process here, which is the resonant annihilation of an electron and positron pair into an X17 particle, or a dark photon with 17 MeV mass. So if you have a positron beam, for example, that impinges on a fixed target, so that the square root of S is 17 MeV, you will achieve the possibility to produce X17 via this process, which has a really enhanced cross-section and a very narrow cross-section, because you're talking of a resonance with a small width, because it depends, talking about the visible scenario, so the width will so depend on epsilon square, so very, very narrow particle. And so we have a process that maybe we can try to use to tune, for example, the energy of a positron beam to produce a particle this way. This process is interesting not only for the fact that it is narrow in terms of cross-section, so we need a very specific energy of a beam to achieve it, but also because at a better scaling with respect to alpha electromagnetic, for example, with respect to the A prime Strahlung that HPS uses and we so uses for research. So we need a positron beam which has an energy of order should be 390 MeV. So not much energy, and this can be achieved with a very small accelerator. You don't need a large collider. And this what was trying to do the Padme experiment. So this is a very small experiment in Italy at the Laboratorio Nazionale di Frascati, and the Padme experiment actually was already taking data when the X17 anomaly was observed, but they were using a technique to search for invisible decay of dark photon. But when they saw this anomaly, they decided to modify a bit the setup of their experiment and move to a search for a visible decay with a tuned beam energy, so to produce this positron beam, this X17 particle via this resonant annihilation. So the setup you see here, this shape, is due to the fact that in principle there was a magnetic field here to bend particles to search for the previous strategy used by Padme, but now they're not using any magnetic field. They simply have a vacuum tube, an active target which measures the position of the impinging of the particles. We'll see why later. And you have this beam, positron beam, impinge on the target. You hope to produce electron-positron pair via this process, and then you measure in an electromagnetic calorimeter the two particles in a similar manner of what HPS did. So this is a photograph of an experiment, just to give you an idea, really the small scale of what we are talking about. This is an experiment apart obviously from the beam, the detector can stay in a small room. And what the principle of the measurement? So we saw that we can produce, if it exists, this particle via this process. But then there are many processes of a standard model that result in annihilation, that from the annihilation of an electron-positron pair produce an electron-positron pair. Simple annihilation where you mediate with a standard model photon result in an electron-positron pair. So if you just measure at one beam energy and you count the number of annihilation that you have, you simply will see a number due to the standard model processes. But what we thought to do was to basically perform a scan in energy around what is the mass of the X17 particle, or more precisely, what is the lab frame energy of a beam that in the center of mass frame reproduces the square root of S, which is the mass of X17 particle. If you do so, what to expect is that at some point while you scan and you change the energy of the beam, going from, for example, we started from 350 and went up to 400, you expect to see at certain point an increase in the number of counts due to the fact that you start to achieve, to be possible to produce dark photon X17 via the resonant annihilation. Of course, we are talking of an increase of count which is order of percent with respect to the standard model, let's say, background, the normal annihilation. So really need to control in a precise way your detector, and you hope the detectors to be very stable. But here, for example, in the plot, you have the variation in the count from this resonant annihilation. So when you change the energy of a beam with two different strategies. So they thought to two strategies. Here is not the energy of the beam, actually is the square root of S, so the mass of the chi particles. So what you expect is to see an increase in the count from the dark matter process of up to an order of 100, which I remember is on top on a stable background, which is much great. So you have to keep it controlled. So this is their strategy, their idea to search for this particle, and this is the reach that they hope to achieve with a run of 10 to the 11 total positron on target. This is a conservative scenario where they do a scan which is a bit larger, so from 265 and 297 MeV lab frame energy of a beam, and to scan divide this range into 12 beams of the energy of a beam. Then they also thought of a more aggressive technique, aggressive scenario, so a bit more statistic, and most of all a narrower range around the X17 resonance, and a larger number of beams. So basically scanning this resonance with more precise, more fine beams. And you can see the reach expected sensitivity is what is enough to go from what is the result from Chloe here and an A64, which are the two experiments that up to now are constraining the X17 parameter space. And so they hope to close this window using this technique that will not exclude very large amount of parameter spaces, but will exclude the region which is of interest for this anomaly. So this is something a bit different from what usually done. They've taken the first data, and we are going on with the analysis, which is complicated. So maybe soon we will have an answer if this X17 is really a particle or just some nuclear anomaly. Okay, so this was the last thing I wanted to say for the thin targets before moving to the beam dump experiment, which will be the topic of this lecture main. And so the idea here is that, as I think is clear from the last lecture, is that for this thin target experiment, you need really to go up with intensity of the beam to be able to reach those regional parameter space where the coupling are very feeble. But you cannot do so. You cannot just increase, for example, the current of the beam, because on one side you will kill your detector with radiation. On the other side, the rate will be so high that you won't be able to trigger anymore. So in principle, you will need something allowing you to go up with the rate, but without having to save, to analyze a lot of events that at the end of the day are standard model events. For example, if you think of the invariant mass spectrum of HPS, just a larger spectrum of standard model things on top of a small peak if it exists of a dark photon. So we need to filter somehow. And there is a physical way to do so, which is a beam dump experiment. So what you do, you have your beam, which can be beam of electrons or protons or whatever, and you make it impinge on a fixed target. So here everything, many things happens, shower, electronic shower, hadronic shower, production of particles, we'll see later. And you may also produce, for example, dark matter particle. But then you put a shielding there to shield all what is coming from standard model, so muon, neutron, whatever. And after the shielding, you place a detector to see the signature for the interaction of such a particle from dark matter or the dark sector region. So in this way, basically, the intensity is being dumped on the dump itself, which can go up in current as much as you want and as you can, and you don't have a large rate on your detector. So basically what you are doing, if you think of a dark matter model, is basically producing like a direct search where you produce your dark matter wind, you make it impinge on your detector. So this is the basic idea. Usually the typical dimension length of this experiment is that you have your detector located at least order 10 meters behind the dump, but more commonly order of 100 meters. The beam of energy, the beam energy varies from 10 to 100 GeV order of magnitude, and there are different possibilities. You may have decay volumes if you think that your particles from the dark sector may decay or not. You can vary the distance, the shielding, and so on. Before speaking of experiments themselves, I want to describe a bit more in detail what happens in a beam dump when, for example, you have an electron beam, high energy electron beam impinging on it. So, as you know, what happens is that you produce an electromagnetic shower because your positron will irradiate a photon which may convert to electron-positron pair and so on. So, in terms of what is the radiation length, you will see the number of particles increasing, and therefore the developing of this shower of particles. And so, inside your target, your beam dump, you have not only the particle of the beam, but many other particles that produce electrons, positrons, for example, but also photons and muons. And therefore, in order to really quantify how many particles are concurrent to the production, for example, like dark matter, we need to introduce a quantity that is called the track length or differential track length. This defines basically the average path that each particles within the shower do in an energy range which is between E and E plus T. So, for example, if you integrate between 0.2 and 0.3, this is a fraction of the energy of a particle within the shower with respect to the initial energy of the beam. You will integrate, you will get a number which is how long is the path on average that the particles within the shower do at that energy, so in that interval of energy. So, for example, this is the differential track length for electron and positrons if you have an electron beam that impinges on a thin target, or thick target, sorry. So you can see that you have obviously a large track length for electron, but also many positrons, because as I said, you produce a lot of positrons in your shower, and so you have, in particular at the lower fraction of energy of the beam, a significant amount of positrons. So basically, what this means that a thick target experiment is not only allows you to go up with the intensity of the beam, but also that a single thick target event may be seen as many thin target events where you have different particles at different energy. And when you are interested in producing particles that are feebly interacting, that you really don't know, you want to explore different possibilities, this is maybe very, very, very helpful. So, for example, you can have access to different production processes, not only the A' Strahlung, that is considered mainly for the thin target, but also annihilation where you have production of a dark photon associated with a photon, but also the resonant annihilation that Padme itself was trying to use. So here, these processes, you have a cross-section. You see that there are differences depending on the mass of the kind. It's not very clear to see, but anyway, if the dark matter party candidate produced here at large mass, the energy, the cross-section is peaked at large energy, otherwise it's more flat. Here I have this cross-section, will depend on the fact that in the center of mass frame, the photon and dark photon go back to back, along with the, prefer to go along the direction of the beam. And here you have a bright Wigner, so the cross-section for a resonant production. You can see that also apart from the shapes, also the scaling is different due to the Feynman diagrams with the result from this production. So you have, in particular for alpha electromagnetic, alpha to the third, alpha to the second, alpha for the resonant production, which means that this is where it is kinematic available, it is dominant. And we will see this in the result of the experiment. So to summarize, for example, if you want to know how many particles you produce via this resonant annihilation in a thick target electron experiment, what you need to do is just to take your track length of positrons and average it on the cross section, and then you get the number. So what this means? This means that a thick target experiment is doing for free a scan in the mass of the dark photon, for example, because if you have particles in the shower that goes from the initial energy of the beam to zero, basically, then you are scanning masses, energies, and then therefore masses in the center of mass frame that go from some maximum to a minimum. Obviously, this means also that the energy of a particle of a dark photon, for example, is bound to their mass, which is another important interesting thing. Okay, so first experiment of what I want to talk is a E137, which is a very old experiment running, I think, in the 80s, which was optimized not for dark photon search, dark matter search, but for axion-like particles. So anyway, particles that are thought to be long-lived and feebly interacting. This was an experiment performed at SLAC in the US, and they simply dumped 2 times 10 to the 20 electron on a beam dump at 20 GeV. The dump was basically a water-filled beam dump made of aluminium. And then the detector was on the side of a hill that acted as shielding. Then after a few hundred meters, you have your detector. So they expected basically ALPS particle to be produced here, travel through the shielding, and then decay in this region here. So they hope to see the decay product of the ALPS in a detector, which basically was a calorimeter made of plastic and lead, plus some tracker to define the direction, coming direction of the particle. They made the experiment in the 80s, they did not see any signal. So what had been done in the last year, given the rise of interest of the theories of light dark matter, to reinterpret this null result in the theory of dark photons. So this has been done in the last year. Obviously, you can consider the production of dark photon given the electromagnetic shower produced inside the beam dump of E137. In this case, also, you can think of a long-lived dark photon that, exactly as in the ALP case, travels through the shielding and then decays in front of the detector, and you can see it. So reanalyzing, reinterpreting the result of E137 in this scenario, they were able to put constraints, and here you see the shape, typical shape that we saw in the last lectures regarding the beam dump experiment, and exclude a couple very low down to epsilon equal 10 to the -8. So here you have this shape, and now we can see from what it comes. So here the coupling is larger, so goes up, so you produce more dark matter particles, but the dark photon is short-lived, and therefore it decays inside the shielding. So if you had produced it, it had decayed inside the hill. You don't see the decay product, and this goes up in this direction, since if mass goes down, also the gamma of the particle at the same level of energy goes up, and so it leaves more. So you can see particles, larger coupling for small mass particles. On the other side, when you go down to a certain level in epsilon, you simply does not produce any more this dark photon, and then your sensitivity is limited. So in the same work where they realize this experiment, they also realize a series of earlier beam dump experiments, which are all in the same fashion. Basically, what changes are the energies, the statistics, the distances between the detector and the beam dump, the shielding, and so on. And we were able to put this limit, which are still today quite strong in the scenario of dark photon. But the experiment was interpreted also in the invisible scenario, because you don't need necessarily a decay to visible particle to detect dark matter, but you may think of the scattering of a dark matter particle inside your detector. And so also in this scenario, the experiment was realized, and it was considered for scattering inside the detector an elastic interaction with the electrons of the detector. The result, therefore, in a transfer of energy to an electron and an electromagnetic shower again inside your detector. And they placed the limit in the scenario. And you can see that even here the limits are quite interesting. This wheel shape here comes right from the resonant production. So this line here is due to the Bremsstrahlung production of dark photons. But here, what dominates is the production via resonant annihilation, because you're doing your scan in energy. And if you look at when it starts and when it finish the dominance of this process, here you have an energy which corresponds in square root of s, a mass which corresponds in lab frame energy of the experiment 20 GeV, which is the maximum energy of a beam. And this is 1 GeV, which is the threshold they adopted in the analysis to define if the signal may be a ALP signal. So this proves this experiment is very old, may be competitive still today for this parameter space. I have to say that this is a bit old and things have gone down a bit, and A64 in particular covered this region, but still, this is an interesting result. Okay, we move now to a future experiment, another beam dump experiment, that therefore has been optimized for this search. So, in particular for the search of dark photon in the invisible scenario, so searching the scattering of this particle. So, this experiment has been proposed at the Jefferson Lab, and the idea is to use 11 GeV electron beam, impinging again on a beam dump which is made of water and aluminum. The detector will be much closer to the position of the dump with respect to A137, and there will be a dense passive shielding optimized to scan to stop all standard model particles, so we don't reach the detector, and still some overburden over the detector itself to shield part of cosmic rays and cosmic particles that may mimic a signal in your detector. The detector design is fairly simple. It's an electromagnetic calorimeter made of cesium iodide crystal, which, as we see, the idea was to get them from the Babar calorimeter, because Babar is no more used, and the crystals were basically free, at least at the first glance. So the volume is about ½ meter, so not really large. And then you have LED shielding that we see what it's useful for, and 2 layers of plastic scintillator that are used as active veto. So you want to veto all the particles that come from outside and can mimic dark matter signal. As I said, this experiment is at BDX, is at JLab as, for example, HPS, and it will exploit again the really high current that this accelerator can provide. So we are talking about 65 microamps in what is the whole A, which is the whole of Jefferson Lab, which hosts high intensity experiment. And this would allow to collect 10 to the 22 electrons on target in order of 1 year beam time, which is 100 times what we on 37 did. And also another interesting thing is that since the beam dump of the hole is here, so the detector will have to be placed on a new hole behind the beam dump. The hole still can operate with other experiments, provided that they don't degrade the beam too much, while the BDX experiment run parasitically. So basically you can operate the several experiments at the same time. And it was originally thought that this experiment which is called Moller, which is running for several months without using degrading the beam, would be a good companion for BDX. So here I have a sketch of the new experimental hole, the BDX detector, which is underground because the beam dump itself, due to radiation concerns, is underground, and it will just be a simple hole with the detector. Here you have a more precise sketch of what is the beam dump of the whole A of Jefferson Lab, which is basically a tank of aluminum plates of different thickness filled with water that you need to cool down this target, because you're dumping there really an intense current, and therefore you will damage it if you don't cool it properly. So here you have the design and this 3D vision, but the important thing is that we know how it is done. This can be, for example, included into Monte Carlo simulation that perform the calculation of the production of dark photon, and so you can reasonably know what is your yield of dark matter particles when you make it impinge, when you make a beam impinge on it. So a bit more detail on the detector. Will be made of 800 crystals, cesium iodide doped with thallium, which enhance the light yield of this crystal, that is to say how much light they produce at a given energy deposited, and will be arranged into modules, 8 modules, each 10 by 10 crystal. The crystals are quite long, and as I said, the idea was to reuse that one from Babar. There are thousands of that are not being used in many years, and so why not using them? They are quite big, 30 centimeter long, but here what you care is just to make some active volume to detect make impinge dark matter particles, detect the magnetic shower resulting from the interaction. Why I told before the LED shielding inside between the Vito. This is basically to protect the Vito from the signal inside, because if you have a magnetic shower produced by dark matter particle without any passive materials between the calorimeter and the Vito, it is highly probable that particles from the shower will hit the Vito, and then you are vetoing your event, your dark matter event itself. So, and in fact, the efficiency for the detection of such showers is order of 50%, is dominated by this effect of shower splashback to the veto counters. Here, for example, a signal register from this cesium iodide crystals. They emit a lot of light, but you can see their emission after a particle has passed is quite long in time. So we have a long decay time. Therefore, these crystals are good for our purpose, because we don't expect to have a large rate of dark matter impinging of a detector, but for high rate uses may not be the right choice. Also, we checked how good can be the time resolution, because if you want to use a signal from Vito to reject event, you have to equalize in time your dark matter signal and the Vito signal, and we saw that you can achieve a resolution of order 5 nanosecond time, which is enough for the BDX requirements. Okay, so now a bit on the expected backgrounds of such an experiment. So everything that can produce something similar to a electromagnetic shower inside your detector, it's a possible background, and so that's the case for cosmic particles, such cosmic rays induced, particles induced by cosmic rays, so like neutrons and so on. We can maybe pass through the active shielding and interact with some of the crystals and deposit some amount of energy. So it's really complicated to evaluate this kind of background with simulation, because basically These are due to inefficiency maybe in the vetoes, really effects which are really complicated to include in simulations, and or really rare events, and therefore the only way was to measure it. So what was done, a prototype of a detector on a small scale was built. The prototype included basically all the elements of a big scale detector, and it was used for a cosmic ray measurement. It was left for a measure of some month, and then it was observed what are the position of energy resulting from this cosmic exposure after that you ask for the anti-coincidence of the two veto system, and then the result was extrapolated to the full scale of BDX detector. Here you have the spectra, and here the tail of this spectra after after asking for the anti-coincidence of the veto. And the result is that reasonably asking for a 350 eV threshold, you are background free experiment from the point of view of cosmic particles. But there is another background which is not reducible, which is that one coming from the beam, because even if you have your shielding between the beam dump and the detector, you can rule out maybe all the standard model particles which are charged and neutrons. As you can see from this simulation here, they show the flux of particles depending on the distance from the dump, but for sure you cannot rule out neutrinos, and you are producing a lot of neutrinos because you are producing a lot of muons. Every once in a while you produce mesons which decays in neutrinos, so you have to take into account this. An interesting thing about this the simulation of this experiment is that really you cannot, it's impossible to simulate the whole statistics, because 10 to the 22 electron target will be impossible for any computer or farm to simulate. So what you do, you use some biasing, which is to say in your simulation you artificially increase the processes that you are interested in and try then to reproduce some effective statistic. And this, for example, is a plot of effective statistic of the simulation used to achieve this plot. And in any case, you have to cope with neutrinos. And in particular, the most dangerous background for this, such an experiment is the neutrino-nucleus interaction with an electron neutrino, where you have, as a result, a high-energy electron that basically mimics what is a dark matter signal. So, in some sense, you can say that there is a neutrino floor also for this kind of experiment, because at a certain level of coupling, you have these events. And there is anyway some way to try to reduce them, this background, considering that there is some difference in the kinematics of scattered electron in the processes of dark matter scattering and neutrino charge current. So you can see that due to the mass of the dark matter particles, the neutrino is the electron is always emitted in forward direction, while the neutrino event has also some large angle tail, which you can use the information to reduce the background. In any case, after all the things considered, we know that BDX expects during whole data taking 5 events of neutrino which cannot be reduced. So this is something you have to live with it, and they introduce several uncertainties in the evaluation of the reach and so on. So this is finally the reach of experiment, considering the full statistic that could be acquired in about 1 year. Again, this is not really updated to the last exclusion limit. So, for example, an A64 is now here, but still, this could be a way to achieve the exploration of the thermal target, also for the pseudo-Dirac fermion relic. And this is achieved in particular exploiting, again, the resonant annihilation that here goes from an energy corresponding to 11 GeV and to a mass corresponding to 350, which is the threshold for the detection of these particles. Okay, so since, as I said, the exit is on a proposal level, it has been approved by the Jefferson Lab, but still its future is not sure. What has been done is to build a small demonstrator really small in mass. We are talking of 44 crystals, but using lead tungstate, which is more dense. Since we had to live with a small detector, we did it with a more dense crystals. The shielding is now tungsten, again more dense than lead. And we have 2 layers of active shielding. So we prepare with this detector, and we use it for a dark matter measurement at JLab to prove the validity of the concept and to see if there were some interesting results. So here is the situation now at JLab. You have the B dump, which is enclosed in a concrete tunnel, basically, and there is still no hole because it has not been built to place the experiment. So what was done? Well, 2 wells were dug, and the detector was lowered inside one of these wells at the level of the beam dump, intersecting the possible dark matter beam. So here I have a picture of the well with a pipe bringing all the connection of the detector. We are talking of about 7 meters from the ground level. This is the idea. So in this preliminary condition, we performed measurement at 150 microamp at 2.2 energy of a beam, and we collected what is about 20% of the BDX total statistics. And here you have the result, the exclusion limit, that of course is contained within another experiment, but it's interesting to see that due again to the resonance enhancement, it touches the curve of E137, which is a much larger experiment, which higher energy, bigger detector, and so on. So this is, I think, interesting. Okay, so we come now to what is the future and maybe the state of the art of what we can think now for beam dump experiment, which is SHIP, which is an experiment which has been proposed a few years ago and has been finally accepted by CERN. So this is an experiment that will be performed at CERN, and it is a beam dump that uses proton particles, so not electrons, and it has a larger energy, so we are talking about 400 GeV. So this is really a multi-purpose detector, because in the concept it is beam dump, because you are making your beam impinge on what is basically a fixed target, and then you look at the product behind. But still there are several stages for the detector, and also a large, as we will see, decay chamber, and so it's a very sophisticated effort, which we will target many scenarios of physics beyond the standard model. So this is very interesting. It will be a long time effort, so we are talking of order of 10 years from now, but this is something that is can be looked now at the reference for what will be the search for this physics in the beam dump fixed target scenario of experiments. So here you have really just to have an idea list of what are the physics target of this experiment. For this lecture we are interesting only in particular on the vector mediated dark matter, but still we are going to study really a lot of final states which may result from a decay of many particles from the standard model. So you have neutrino portals, so possibility that dark matter is mediated by neutrino, supersymmetry, scalar mediators, and so on. So also supersymmetry particles. So really a large number, a large and broad scenario, physics scenario for this experiment. So, but now, but for us, we will stick on the dark matter, in particular on the invisible, but also for the visible search for dark photons. So, as I said, this experiment will be performed at CERN, but this is not an LHC experiment because it is a fixed target experiment. Therefore, will be performed at the SPS, which is, as I maybe mentioned the lecture earlier, the pre-accelerator that accelerate protons that are then injected inside the LHC. So this is the top view of the thing. And this accelerator reaches energies up to 450 GeV in protons, and so this is what will be used for SHIP. It's not a continuous accelerator, as in the case of, for example, BDX, but it has a spill structure. So you have a particular for SHIP, a structure of 7.2 spills, where you dump 2 × 10⁻13 protons on your bin dump, and then this process is repeated, and the average power of this spill extraction is ordered 2.5 megawatts. So we are talking really large power, and something that it's challenging, first of all, from an engineering point of view, because many work will be required from the point of view of radiation protection, the infrastructure, and so on. And so you see the total statistic accumulated is 5 times 10 to the 20, which is much less than BDX, for example, but you are talking about a proton beam, and this is very different, because with a proton beam you may access a series of processes to produce beyond standard model particles, such as decay of meson, for example, which are give a lot of yield in terms of dark matter particles, for example. And here is a sketch of what is the dedicated experimental facility for SHIP, which is already existing at CERN, will be dedicated completely to SHIP in the future. Okay, here I have something about the target, which is the bin dump, because they call it a target, but it's a bin dump. So it's basically a series of layers of different materials. We cannot use aluminum because now the power dumped here is really high. It's a much more sophisticated dump, you can say. It's a total of 10 nuclear interaction length, which correspond to 120 centimeter, and it's made of layers of tungsten and an alloy called TZM, which is composed of molybdenum and tungsten, and it is the face is 30 by 30 centimeters square. So you have 13 layers of this alloy and 4 layers of tungsten, and they again are interleaved by water cooling, which is necessary to dissipate the huge power deposited in this part of the experiment. And here we have which is very interesting, the energy deposition within this target per SPS spill. So one spill of 7 seconds deposit energy that is order of almost a kilojoule per cubic centimeter inside your target. So it's something that really important. Okay, so now another thing that makes SHIP really different from a traditional bin dump experiment is that you cannot just rely on a simple shielding made of passive material, because if you produce muon, for example, with 400 GeV, you will need really many meters of lead to stop them. So you have to think of something else, and the answer is to build a magnetic shield which is able to bend this flux of muons in particular that are produced inside the target. So we are talking of order 10 to the 9 muon per spill. So you have to somehow deviate them, because otherwise they completely blind your detector and produce a lot of background. So the idea was to arrange a series of magnets, so to build some geometry that can deviate the muon from the trajectory of the detector. And here, for example, in this plot shows the top view of the muon shield in 2 colors represented the different direction of the magnetic field entering and exiting from the plane. So they had to find a way, with a bit of puzzle, to arrange a condition where with the magnet you are able to reject these muons independently from their energy, which is really something challenging because you produce a lot of different energy muons, and you want your geometry to be effective in rejecting muons at different trajectories. You see, for example, here if two trajectories are rejected in a different way because their energies were different. So there is a first magnet which is responsible for basically dividing positive and negative muons, and then the other magnet completes, let's say, the elimination of the muons from the trajectory of the detectors, which is downstream of the shielding. So we are talking of a big object because it's 20 meters, 28 meter in length, and weight almost 300 tons. Here you have a 3D representation, but yeah, this is the shape that we have to produce this kind of magnetic field. Okay, so after all this part of shielding and the target itself, we have the real detector. So this is a two-stage experiment, you can say. So you have a first part which is dedicated to neutrino physics, basically. So I won't go into detail about that. But since you produce a lot of tau neutrinos, it's a good chance to exploit this flux to study neutrinos. So you have a magnet, a spectrometer, and some emulsion to see the tracks of the products of the interaction of neutrinos. And then you have what it is another challenging from an engineering point of view part of a detector, because it is a vacuum vessel that it is used to have to give the produced particle from the dark matter or dark sector or beyond standard model scenario to decay before detecting the decay products in the detector itself, which is here. This is a really large pipe, which is almost 80 meters long, and the original idea of the collaboration was to have it with a vacuum inside, because if, for example, you have a neutrino which crosses the pipe and it interacts with something inside the pipe, gases, and produces some particles, then you will mistaken this particle, you misidentify this particle and think that they may come from a decay of some standard dark matter particles, while it's simply neutrino interacting inside the pipe. Now, I mean, they are a bit on the fence, because realizing such a big structure completely with vacuum inside is really complicated, because under the atmospheric pressure this thing will probably collapse under the pressure. So this is something that is still being discussed. As I said, an experiment which is being approved, but still the concept is being discussed. And to make things more complicated, you also want to veto all the possible particles that from outside enter the decay volume and decay inside this decay volume or make some interaction. So on top of everything, this pipe basically will be also surrounded by some active veto, and the idea for now is to do it with a liquid scintillator. So it will be basically a tank with a hole inside. You have a scintillator outside, and we talk about 80 meters, so we'll have to instrument all this 80 meters to be able to detect a charged particle that enters from outside and then does something that you don't want. And then finally, you have the main detector for the searches for physics beyond the standard model, which is, again, a spectrometer which does all the things that, for example, the LHBC detector we saw does. So let's say measure the momenta of the particles, measure their energy, and so on. So it is a multi-stage, you can say, detector. You have some strobe tracker, and we saw them in a second. Then basically your magnet and some timing detector, some calorimeter to measure the energy of the particles, and finally a muon detector, because muons are the only particles that survive on the detector. this is just to give you an idea of the scale, and that's why this experiment, so we need some time to be to be realized and put in operation, because the detector, so this is the part, for example, dedicated to the tracking and to the spectrometer for the measurement of the momenta of the particles resulting from a decay in the decay volume, it's quite large. And here you can see these that are the straw tubes responsible for the measurement of the position, impinging position of the particle. So these are really simple detector. These are tubes which have a conducting wire inside, and they are filled with gas. When a particle, charged particle, passes through one of these pipes, ionizes the gas inside, and so since there is a difference, a potential difference between the wire inside and the tube itself, you see a current, and you know that something passed there. So if you put many of them in different direction, you can reconstruct the passage of particle through them, and they are much more economic than, for example, silicon detector, such them used by LHCb or other colliders, that on this scale would be complicated to use an instrument. So this is the idea. And here you have between the two layers of these straw tube detectors, you have your magnet that bends the particle, so you are able to measure the momenta. Okay, so we come finally to our interest, main interest, which is to say what will be the discovery potential of such an experiment in the scenario that we have discussed and talked of up to now. And here is the result. So we are talking of an experiment that will be able to set limits both in the visible and invisible decay scenario, because you have this decay volume where you can have your dark photon decay and see the, for example, leptons resulting from the decay, 2 muons, for example. But also you have a detector where your dark matter particle can interact, and so you can measure, as in case of VDX, an electromagnetic shower, and therefore you can estimate a reach for both cases. I have not talked about the production mechanism of light dark matter with a proton beam. There are several possibilities, which depends, more or less relevant depending on the mass you are exploring. If you are in the light dark matter range, which is below 1 GeV, basically, the most important processes are the Bremsstrahlung of protons, so proton Bremsstrahlung. And for high energy, instead, you start to have importance from the Raelian on QCD processes that happen on a quark level. So here is the reach, and you can see it covers basically all the Van Dam's experiments that I've shown before, and also moves a lot to the large masses, because the energy of the beam is much larger than the one of the old Van Dam experiment. It's interesting to know that the limit here is not due, as in the case of 37, by the fact that the coupling to fiber, you do not produce your dark photon, but it's due to the fact that the dark photon are too long-lived, they go past the detector. So still the intensity of the beams is such that you can still produce particle here. And on the other side, you have your reach in the light dark matter scenario, which is now compared to which are the most important for now experiments, which are NS64 and Bavari. You can see that if they will be able to conclude and achieve the program that they scheduled, this experiment may be probably cover large part of the thermal target which has remained. Apart from region in low masses, where due to the fact that the mass of the dark matter become very light, and there are some effects due to the selection trigger and the selection of events to reject the neutrino backgrounds, for example, that make you lose efficiency for this region. So that's it. Here you see this shape here is due, you see it's at about 200 MeV mass of the Chi particles, but this is taken in a scenario where the mass of the Chi particle is 1/3 of the mass of a dark photon. So in terms of dark photon, this would be a mass of 700 MeV, which is the mass of a raw meson, which is vector bosons exactly as the dark photon, and so you have a resonant production that comes from a sort of resonance that enhances your mixing, your yield of particles in correspondence of this precise mass value. So this is the result for now for a ship, and we'll see. Well, we need many years because before the experiment operates, but for sure it's one of the most challenging proposals in this field. And I'm done.
Thank you. So now is coffee break time, so we will come out with the question after the talk from Javier, and we will have time to discuss about that, okay? So thanks, Luca. I know that everybody should be tired, but remember that the lectures start at 9 o'clock, so try to arrive 5 minutes. We are very nearby the hotel, but arriving at 9:05 does not make sense, so leave 5 minutes before and you will arrive on time, and this is very important, and we have only, today is Wednesday, 2 more days, 2 more mornings, so make the effort. The second point is who is going to do the experiment, the lab experiment 2, that is the Jan 4, and needs to put the virtual machine. The professor is on the second floor of the other building, and you can go there and make a copy before lunch. So you can leave from here, go there, and you will be ready for 2:30. What else? So what do you need? Okay. Today we will make the same schedule as we did yesterday, so that means that after Javier talks, we will have 30 minutes, 20 minutes for questions, and then we will leave for the USP as we did the day before. We meet there and we make group of 4 to take the Ubers. Go there immediately after the discussion, so we can move to the USP on time. And also, if you are a Brazilian and if you know how to go to USP, let us know when we are there, because it's much easier to split the Brazilians in different Ubers, just in case. Okay, so we will continue with Javier now, if he's ready. Microphone, please.
Okay, can you hear me okay? Yeah. Okay, so the third lecture. Today we're going to discuss another technique that goes slightly to lower masses for the dark matter candidates. That is the cryogenic crystals in general, but we are also, if we have time, also discuss some new idea with cryogenic superfluids also. The candidates that we will be looking into are, well, still the standard WIMP. Many of these techniques started for the standard WIMP searches, and then they evolved into looking for other candidates in lower mass ranges through the electron channel, because essentially everything has electrons in them. So some sensitivity, it's always there. So if you are able to lower your threshold, you will still be able to do these kind of searches, okay? So again, this is just a reminder. What are we looking for in a target? Now, we discussed this when we were looking into which noble gases or noble elements were good targets for dark matter searches. The same will happen here with solid state things like semiconductors or crystals or things that produce some kind of signal. Again, these things apply. We want to have nuclear recoil, electron recoil discrimination for the standard WIMP searches, because the biggest rate is going to come from the interaction of WIMPs with nuclei because of the coherent enhancement of the cross-section. Then we want heavy targets, but again, heavy targets are harder to match kinematically with the dark matter candidates, so you will have smaller signals. At the same time, for this is also very, very critical that we have things that we can purify a lot and remove all the radioactive isotopes in them. So that will limit the amount of materials and elements that we can use for our detectors. Then, for the light dark matter, the problem is not so much having a large nuclei, but having something that you can have a very, very low threshold. So again, here you can go to elements that are semiconductors or semiconductor-like, and those will have a band gap that is relatively small. But the problem is that if you keep moving this thing to smaller and smaller energy differences you need to provide in order to excite one electron to see a signal, that will naturally have more dark count events that happen just because of thermal fluctuations. If you have something at a temperature that is different to 0, you will have thermal fluctuations, and some of the electrons will be seen as signal even though there is no external radiation coming into your detector. Okay? So this is also one of the motivations why many of these crystals and solid-state detectors go to cryogenic temperatures to remove all this energy excess that you have within your sensor that produces a signal even if you don't see anything from outside. And that is particularly important for phonons. I don't know how familiar you are with phonons. I'm not going to go into a lot of details with that, but here I'm going to discuss what's the simplest way of use something like this, a calorimeter, to look for dark matter or radiation in general. Okay? In this case, you have an absorber that is made of a crystal. Okay? We don't need to go into details into which crystal. It can be silicon crystal, germanium crystal, or things that are a lot more exotic. But you have a piece of material, okay, that it's cooled down, let's say, to a temperature that is very close to the absolute 0. So you have a thermometer here that is the link that is in between this absorber and a heat sink that is at millikelvin temperature. So in the long term, this is going to be everything thermalized at the same temperature that is going to be in the order of millikelvin. Okay? And you have this thermometer here that you are recording the information over time, and you see that you always measure 0. Okay? Then at some point you have external radiation, okay, that can be a WIMP or something different, that produces deposits some amount of energy in this crystal. It could be through a nuclear recoil, or it could be through an electron recoil. What is important is that it transfers some of its kinetic energy to one of the elements inside the absorber. Okay? And then what happens? When you have excess energy in one position, localized in space in one position, this will tend to just be homogeneous, uniformized, just thermalized. Okay? How does this happen? There are several ways. One way is radiation, again, like scintillation. Okay? So you have something that is excited, then that relaxes, and then it produces photons that go away. That is one possibility. What are other possibilities? I know we are all tired, but yeah. What are other possibilities? Okay, so the other possibilities are, for example, again, radiating other stuff. Okay, you can radiate another electron. You can have an electron that moves through the material and produces secondary ionization because it hits other electrons, and then in this way the energy is split among other particles until it gets completely uniform. But the main way energy is lost in most materials is heat. Okay, what is heat? Heat is just movement in the element, in the nuclei. There are vibrations in the nuclei that you have in this material. Okay, and that is what I'm calling phonons, because you can describe these vibrations in the lattice as things that have similar properties to particles, although they are not particles, just vibrations in this net of atoms that you have there, but they can still be described pretty much as particles. Like if you have I don't know, string, you do like this, then that thing propagates similarly as a particle. Okay? Okay, so you will produce heat here. This heat, because this is energy, this will just bounce around the absorber, okay? And at some point, it will go through your thermometer, and this link between your main detector and the heat sink, okay? And when that happens, this thermometer will rise its temperature because this thing here has a relatively small volume, so a small amount of energy, a small amount of heat can produce a large change in temperature in this thing, okay? And then this thing will go up in temperature, And the difference in temperature will be given by the amount of energy that you put inside this small thermometer divided by the heat or thermal capacitance of this thing. Okay, very similar to what you have with a capacitor that you put, some charge and it changes the voltage. Okay, so this goes up, but over time the phonons keep bouncing around here and they flow through this link to the thermal bath, and you will have a signal that looks something like this. Okay, so this is very nice because everything produces heat. It's the thermal death of everything. Okay, at the end, we are all going to be heat. Okay, so you will have here a signal that is kind of guaranteed if you transfer some energy into your target material, but then you need to be able to record this, okay? And this is not going to be simple because we are looking at millikelvin temperatures, things that need to be read pretty fast, and then there comes the question of how do we build a thermometer that has microkelvin resolution, okay, and also a time resolution in the order of milliseconds. That is not easy. If you tried measuring your temperature when you had COVID at some point, you know that it takes a long time and the reading is really bad. Okay, so how do you do that? Well, you look for things that change their behavior a lot when you change the temperature. Okay, and when these things happen, one situation where these things happen is when you are close to a phase transition. Okay, for example, when you are going from water to solid in ice. Okay, you have there that a change in very few degrees changes dramatically the properties of the material that you are looking at. And in this case, what we are going to use is the transition between superconducting and non-superconducting states in a metal, okay, or any material. So in this transition, you go from a resistivity that is close to zero, okay, or zero, and to something that is not zero. In this case, around 100 milliohms. That I know milliohms looks small, but it's well within the reach of technology to measure that. So you will have here that a change in a few millikelvins, okay, will produce this huge jump in resistivity. And in this range, it behaves close to linear, okay, and even if it's not linear, you can calibrate this. But let's assume that it behaves close to linear, okay, and you operate your detector at at this temperature, okay? So you select the thermal bath here. So this thing is at the operating temperature in which your thermometer changes the phase, okay? And that's the only temperature that you can operate this thing at, okay? And you have to be very precise. But you do that, you get there a resistivity, let's say, of 50 milliohms, and then that's your operating point. Whatever deviation you have from that is the temperature changes that go through your thermometer, okay? And you can measure a resistivity pretty fast, okay? So this has the two properties that we wanted from our detector. This is just one of the options that are being used for thermometers, but it's the one that we are going to stick because I don't have a lot of time to discuss other, but we can talk about those other options during the coffee break. But this is the one that it's most widely used. Okay, so just summarize, you have energy in the absorber that it's in the order of keV or so. Then you have a temperature rise in this transition edge sensor. That is the name of this technology. That can be in the order of microkelvins, and the resistivity changes in the order of milliohms. Okay, so now we know how to do this. And for you to get an idea, this is nothing super fancy, okay? The transitions air sensors are also very nice because they are super simple. This is a picture of CREST 3. This is the experiment that I will be using as a benchmark to explain or tell you about a little bit more about these technologies. Then I'm going to move to another experiment that is called Super CDMS to talk about other slightly different detectors. There are lots of experiments and variations on this technology. I'm just going to stick to one to talk about the detection principles. Yes?
So I have a question about the previous slide.
Yes.
About the resistor. So basically we have this resistor that changes linearly within a range. So it means that we know beforehand, before doing the experiment, more or less what is the range of
Yes.
temperatures.
Yes.
And how do we know before using, I mean, in this case, we would need another thermometer to estimate, right?
Yes, so I mean, all these things have been extensively calibrated. And the thing is that you don't need to calibrate each individual TES, because the thing is that the resistivity and the transition only depends on the properties of the material. So let's say in this case, you are using a tungsten thingy, okay, to measure what's the resistivity of this thing. So that is something that never changes at all. And you can measure the resistivity and the properties of these things with systems that are much higher and in which, I mean, a lot more convoluted. But once someone has measured this, then you are good. But how do they calibrate and do the original measurements to say tungsten has these particular properties? I don't know. I need to look into that. But that's done by material scientists, and I don't know what's the technique used there. But this has been measured with extremely high precision.
Oh, okay. Thank
you. But yeah, so in this case, for CREST, so this is the white thing here is the absorber that we had in yellow here. Okay, so this is the crystal where you be looking at the interactions with radiation. And this thing here is the transition edge sensor. That here is a close-up. So what you have is this dark gray area and this other dark gray area that are just metal aluminum foils that are deposited on the crystal that you use for two things. One thing is just to connect this to a bias on one side and the other one to a bias on the other side. So you have a current flowing through this, and then you can measure what is the resistivity of this thing. This thing is just a resistor in a way, okay? And these things are large also to be able to collect the phonons more efficiently. So remember that I told you that you will have these vibrations, phonons, bouncing around the crystal until they find their way out. And the way they find their way out is by hitting one of these aluminum foils. When they hit that, then that transfers the heat into this small part that is the transition edge sensor itself. Okay? They are just collecting heat and moving it into this thing. And then the way out for cooling out this huge crystal is just a hair-like cable that is connected to the tungsten rectangle there. So all the cooling is done through that, which is crazy, okay? So these are called wire bonds and are cables that are the size of a hair or smaller, okay? So you have your crystal here, things going out. This hair here is the thermal link, that is this thing here, okay? So this is very nice. Oh, just for completely, this thing here is a heater that they connect to an outside source in order to introduce pulses of heat and see that everything is working. But it's not a detector. It's just there to cross-check that everything is connected and looking good. Okay, so you see that the design of this, it's very, very, very simple, okay? So how can we improve on this? I told you before that heat is one of the ways that you can distribute the energy to get to an homogeneous state, but there are others. As I said before, we have possibility of producing photons there. So we will always have phonons, okay, in an interaction, but I don't know if you can see that, but these ones, here it says photons, okay? So you will also produce light. And many of the materials that are selected for this are so that they also have properties of a scintillator, okay? So you can excite the electrons there, and then when they de-excite, they emit light, and you can place another sensor close to this one to be able to see those photons. And the reason behind this, you probably already guessed, is that it's twofold. On one hand, having more ways to collect the energy helps you to actually see a signal, okay? Because if you are losing all the photons, that they just go away, then the signal is going to be a fraction of the total energy, just the phonons. If you collect both, then you have more chances of seeing something and going to lower thresholds. The other thing is that, again, you want to have electron recoil, nucleon recoil discrimination. And remember that in noble liquids, what we have is that the amount of light that is produced compared to the amount of ionization that is produced depends on if it is a nuclear recoil or an electron recoil. Well, the same happens here. The amount of the photons that are produced compared to the amount of phonons that are produced depends if it is a nuclear recoil or an electron recoil. And what is very neat about this idea also is that this detector, that is a light detector, okay, essentially uses the same technology as the main detector that you have there. So what you do is you place a different material that has the capability of stopping these photons that are coming out from your main absorber, okay? And this is typically a different material because you want your absorber to be transparent to the scintillation photons that are produced, but if this thing was made of the same material, then it would be transparent too. So you would not be able to see those. So you select a different material for this thing that is not transparent to the photons, and then you look at the heat that is deposited by these photons into this second detector or absorber, okay? So here is an example of the two signals by a crest detector. So you have the phonon signal, that is the one in red, and then in coincidence, the light signal. Because look at the time scale of this. This is milliseconds, so these are relatively slow detectors. And the light, because we are talking, I mean, takes essentially no time from here to here, because these are detectors that are this big, okay? So this idea has been implemented, and here is another version of the crest detector. The crystal is here on the back, okay? And this rectangular thing here, you can guess, is the light detector. There you have a transition edge sensor coupled to the thermometer, okay? And again, you can see that all this is enclosed in copper. The reason for that, you already know, is that copper is one of the things that we know how to purify best. So a lot of things are made of copper because there are no radioactive isotopes of copper, and you can do a chemical separation of copper of everything that is radioactive, or most. So the crystal that they are using, you can see here, is calcium, tungsten, oxygen. So this is an exotic crystal. It's not a single element. In this sense, it's similar to the gamma crystals, okay, that you have many different targets there with different number of nucleons in them. So you are able to use this thing as a multi-target target, okay? Because you are able in this way to have things that are heavier to see heavier masses for dark matter candidates, and you have nuclei that are lighter to be able to see or have sensitivity to light dark matter candidates where your flux is higher and you don't need as much, okay? Enhancements in the cross-section. And the size of this thing is a few centimeter cube, okay? So we are talking about really small thingies here. And here, what I'm showing, this is the theoretical expectation, okay, for the electron recoil, nuclear recoil discrimination. In the x-axis, we have the energy that is deposited or goes into the absorber. And in the y-axis, this is light yield, is just a fraction between the total energy and the amount of energy that goes into light, okay? And what you can see is that, well, you have different regions here, and some of these is because some of these regions correspond to tungsten, some of these regions correspond to oxygen recoils, okay? So these two lines here are nuclear recoils from tungsten and oxygen, okay? And then the brown region on the top is the electron recoils, that those don't depend of which, I mean, where the electron came from, if it came from an oxygen or a tungsten, okay? So you can see that these two are very separate, very easily discriminated at relatively high energies, but when you go to low energies, everything becomes mushy. And that is reasonable, okay? Remember also this happened with the novel liquid detectors. When you go into low energies, you only had essentially one signal to look at, and then the estimator for the ratio of these two things doesn't make sense. The fluctuations are huge, so you don't have any discriminating power at very low energies. And unfortunately, that's where you want to look at, okay? But still, this provides a very powerful tool to identify your backgrounds and also to understand how your detector is working, and also at some energy range to provide discrimination, okay? This green band here is alphas, okay, that behave something like in between the two. So if you have a radioactive element that decays and produces an alpha, it's not exactly the same as this heavier nuclei, but it behaves more like a nuclear, but much lighter, so closer to an electron recoil, okay? So that was calculation. This is data, calibration data that they took. And you can see that it works pretty well. I mean, it's not perfect, but it really has a big discrimination power at higher energies. But when you are going to lower energies, as expected, everything becomes less clear. Still, you do have some discrimination power, but it's the spill from the electron recoil into the nuclear recoil is big. Okay, so it's much harder to get a clean sample. So this was a calibration run. This is not what they used for looking for dark matter. Okay, so to look for dark matter, you place the same detector that you have already calibrated and completely characterized inside the shield and run sometime with this and collect data. Okay, and that's this plot. Okay, so now you can see how real data for these sensors look like, and at high energies, okay, no nuclear recoil candidates at all. Okay, nothing. So super clean. But you also see that there are a lot of electron recoil events. And this is just to illustrate something that we've been discussing a lot, that the main background contribution is coming from electron recoils, okay, everywhere. So you can live with a much noisier environment if you have electron recoil, nuclear recoil discrimination. If you don't have electron and nuclear recoil discrimination, you can still have an experiment and there are plenty of experiments that run like that, you just need to be aware that the impact of any radiation in the environment is going to be much larger, okay? So, but what happens when we go to lower energies? So when we go to lower energies, well, what we see here is essentially a lot of events, okay? And even before that, in this region, we already start seeing candidates for nuclear recoil events. Can we guarantee that these are nuclear recoil events? No, we cannot guarantee that. They can just be spillover from the electron recoil channel, okay? But we don't know. So, oh, sorry. Here, okay, I don't know if you can see that, but there is a kind of a lighter shade of black, okay? Here, this is the region that they use to look for dark matter. So again, they are playing the same kind of trick that we discussed before, that you can pay half or more of your efficiency in order to get a cleaner sample. So what they do is exactly that. So they say, okay, I'm willing to only consider the nuclear recoil events that appear in this shaded area, reducing my efficiency by about 50%, but I'm going to reject all this trash that is here, okay? So I'm going to have a much, much cleaner sample to look for WIMPs. And when they do that, they place this limit. This is a limit that was produced in 2019, so a few years ago. And since then, they have kind of hit a wall. And I'm going to go into details on what happened there, or what happens there. There are some new results from CREST. That is a beautiful experiment. But most of their focus has not been in really improving the sensitivity so far of the experiment, but understanding where these low energy events are coming from, okay? Because that is what is really limiting their reach, their science reach, okay? So here, I'm just projecting all those, I'm just projecting all these events into the x-axis here, okay? And that's what you see. So in gray, we have everything, all the events, all the dots that we had in the previous 2D plots. And in red, we only have the events that are in this shaded region, okay, the selection region. So you see that here we have a huge spike, okay? And if we look closer into that, it looks like an exponential-ish decay. And unfortunately, that is exactly a signal that you would expect from a WIMP, okay? So if you have a background that mimics exactly the kind of signal that you expect for the thing that you are looking for, that really, really kills your sensitivity, because you cannot really move forward if you know that this is a background, and for other reasons, than they are not claiming that this is a discovery of dark matter. But then it really limits your science reach. And they know that this is no dark matter because of many reasons. Because of many reasons, but I'm going to discuss that later on, okay? So they've been focusing on understanding where these things come from. And they tried, over these 5 years, a lot of stuff, okay? So here, this is a slide from the CREST presentation at IDM last week, okay? And they are just showing all the things, or some of the things that they tried. So they said, okay, maybe this is related to the target material. It's not as clean as we believe, or it has some problems. So they changed. Instead of using the elements in the crystals that I showed you before, they used different elements. They grew crystals in their labs, do stuff. They still have this excess, okay? Then they try different techniques for growing the crystal, which can be very, very important, because any defects on the crystal can create intermediate energy levels that then have a different behavior. So this also didn't produce any difference. Then they remove the scintillating materials from the crystals. You can do that, for example, by using silicon. Silicon does not scintillate, just pure silicon. So still the same problem with the excess. Then they started looking at stranger things, like, okay, well, it is true that we have a detector that it's not really coupled to the external world by anything, but that is not real. I mean, that's not reality, because you have in some way to mechanically hold this thing in place. So there are these clamps or holders, okay, that can introduce mechanical stress, or can produce events. Let's say that you have an event here on the clamp, and then that goes into your sensor, but only deposit a fraction of the energy, not the full energy of the event. So that can also produce this low energy excess. So they tried changing these things by different designs that didn't change. They even went so far as to make these holders of the same material crystal that they have inside, and put a transition edge sensor on each of these holders to see if there was any flow of thingy. So the complexity of this started scaling up a lot, but unfortunately they did not really were able to pinpoint what was the problem with this. And none of this really produced any measurable improvement. The idea right now, and I will go back into this later on, is essentially that maybe this is linked to some kind of mechanical stress and relaxation within the crystal itself, okay? It has been known from the beginning of this technology that if you introduce some mechanical stress, you will have fractures and microfractures and things that produce an excess of low energy events. That has been done, but they did a lot to reduce this stress. But still, what they do see, and this is one of the reasons why they know that this is not a dark matter signal, is that in the y-axis is the number of events per day, okay? And in the horizontal axis is just time, days. So these are different runs that they did with the detectors, okay? And you can see that when in these shaded regions, here, for example, they were operating at a millikelvin temperature, at the temperature that they need to operate, 15 millikelvin, okay? And then, for some reason, they raise the temperature to 60 Kelvin to do some work or whatever. And after that, they had a huge spike on these single electron events. And this is already at the operating temperature. If not, you cannot read the transition edge sensor. So this is already at 15 millikelvin. But then you have a very long relaxation time that takes many days, and it's not clear why that is happening. If you make a change in temperature that is smaller, you still, well, it's not super clear here, but changes in temperature that are smaller don't produce as a big effect, but they still produce an effect. For example, here with 30 Kelvin, you see a spike, but not as big as 60 Kelvin. And when you warm up to 130 Kelvin and then start reading up, you again have this huge spike. And this is not the behavior that you would expect from dark matter, so they know that this is no dark matter. But it's also not clear why this is happening, okay? And one of the ideas is that, yeah, there are some internal stresses in the crystal that when you warm up and cool down, well, you know that things change the amount of stress and how these things are distributed. So when you cool down, you may still have some remnant stress that is slowly being readjusted. But it's not clear. But we will discuss this further on in the talk. So now, that was the end for CREST light detectors. Now I'm going to discuss a slightly different technology, but that is very, very similar to the one that is being used by CREST. Okay. the idea here is very similar. Is again, we have an absorber, okay? And as always, we will produce phonons when there is an energy deposit, but instead of selecting a material that produces scintillating photons easily, here we want to select a material that produces ionization easily, okay? So you have ionization here, and if you just leave it like that, those electron holes or ionized nuclei and electrons will just recombine in place, okay? Producing more heat or photons. But if you apply an electric field there, similar to what we did with the noble liquid detectors, the TPCs, then you will not allow time for these things to recombine. You will separate them before they can get together and become neutral again. And then what you will have is that these things start splitting and going to the two different sides of your sensor. So if we now have here our thermometer, then we will measure this spike in temperature. This is the phonons signal. Then, because the electrons drift very slowly, the same as they did in noble liquids, you will not measure any current flowing through this thing yet, or you will measure the steady current that you had before. But at some point, well, all the phonons go away, these things go into your cables that you have there. You have here a current sensor or some way of measuring the charge flowing through that, and you will have a second spike that is related to the amount of ionization. And again, here we will be playing the same trick that before. We are looking to use the ratio between these two signals to have electron recoil, nuclear recoil discrimination, and also to be able to collect more of the total energy that has been deposited there. This is an ICIP detector that is one of the super CDMS sensors that has essentially this design. We are looking at this from the top. This is about this thick, so it's about this size and about this thick. So it's like a pack, I don't know. And all these lines that you see on top we are going to look at those in details, but are ways of collecting phonons and ways of collecting charge, okay? And again, this thing is inside the copper box as usual, okay? So now if we look at those lines from the top in detail, they have a structure that is like this. Each of these blobs has this structure in them. So these are aluminum fins or gold fins, and then these things here are the transition edge sensors made of tungsten or other materials, okay? So these things are collecting the phonons that are produced in the crystal and giving you a signal outside. The same, well, I don't know if you can see that, but in between these lines that are just a string of transition edge sensors, you have another line that is just there as a contact to collect charge, okay? That is producing your sensor. Okay. So, oops. So this provides electron recoil, nuclear recoil discrimination. Another way of operating these sensors is what it's called the high voltage mode, which it is a very interesting way of using these sensors and provides the best sensitivity to low energies, okay? And the way this works is the following. Remember that before we had this voltage that was in the order of a few volts, so this was a relatively small voltage, and the drift of the electrons that you produced and electron holes that you produced in the crystal was small, and you did not provide enough energy to really accelerate these things a lot. But if you keep increasing that voltage to a high number, then what you will have is something that is similar to what happens in a PMT or similar to what happens in the extraction layer in the gas pocket in TPCs, that you provide enough energy to the electrons there so they accelerate and they hit other electrons or nuclei, and they produce secondary signals. Okay, so this produces amplification. And in this case, what you are using is these crashes between electrons and holes and the lattice itself to produce phonons. Those are the easiest to produce. In order to ionize further, you need to provide enough energy to the electron so it can accelerate and hit another electron to be ionized. But that's a lot of energy. So that is in the order of EV that you need to provide. This, in order to produce a secondary phonon by just crashing with nuclei or the lattice itself, you only need to provide milli-eV. So you will produce a huge amount of phonons compared to secondary ionization. So the trick here is something slightly counterintuitive, is that you accelerate these things by applying a high voltage. When you do that, when you apply a high voltage, your sensitivity to actually seeing the original charge gets completely ruined, so you are not able to see the ionized charge directly using your current sensor, okay? But you will produce a lot of secondary phonons. But those phonons that you produce are linked to the amount of ionization that you produce at the beginning, not to the amount of phonons that you produce at the beginning, okay? So what they are doing here is using this technique to measure ionization only, okay? Because also with this huge amount of secondary phonons that are called Luke-Naganov phonons, what they do is also they completely bury the original signal, the original heat signal coming from the primary interaction. Okay? So this big signal that is coming from the secondary phonons is produced by the ionization that was produced in the original interaction, not but by the phonons that were produced in the original interaction. Is that clear? I know. Okay. So in a way, this, although they are measuring phonons, this is just an ionization detector, okay? They are not really having this electron recoil, nuclear recoil discrimination anymore, because you only have one signal, and the only signal that you have is ionization, even though you are measuring the ionization through a phonon channel using this amplification, okay? So the Super CDMS program it's very large. Is one of the largest experiments in the US for looking for dark matters, and they are targeting the WIMP masses around 1 GeV. The reason for this is that for higher masses, well, you completely are dominated by bigger detectors, like the xenon detectors that we discussed yesterday. And for lower masses, this, as we will see, is not necessarily the best technology. But there is a range around 1 GeV masses in which this is the best way to go. Okay, so these sensors, they are going to have a lot of them, okay? And they mixed between germanium sensors and silicon sensors. In this case, because you are looking at ionization at the same time as phonons, you have a smaller selection of materials that you can try compared to CREST, because here you need the materials to be semiconductors, and there is a limited range of options there. Germanium and silicon are the best understood and the ones that industry has the knowledge to produce. Okay, there are other possibilities, but these are by far the two easiest ones, the main ones. So they are putting many of these detectors and interleaving some of the ones that I told you before, the ICPs, that are the ones that are measuring at the same time ionization and charge to be able to have, ionization and phonons to be able to have electron recoil, nuclear recoil discrimination, together with other detectors operated in the high voltage mode. They do this in order to have a wider range of sensitivity to all the masses that go from lower masses to higher masses. Okay, and they place these things in copper towers that look like this. They stack a lot of these things in one tower, and they have many of these towers all together that need to be operated at around 50 millikelvin, which is very low, so you need a huge infrastructure in order to be able to cool down all this mass, that is about 30 kilograms in total, of target material. If you include there all the copper shielding, casing, and stuff, it's a lot of mass, a lot of material that you need to cool down to millikelvin temperature and extremely stable. So all that is placed inside a copper cryostat, okay? That is then placed into a neutron shield, and then that is placed into a second lead shield, and outside another shield that is made of polyethylene, also to shield from environmental neutrons, okay? And you have some openings there that are for the dilution refrigerator that is used to cool down to millikelvin to the electronics that is on the other side. So this is a very big program, and this will start commissioning likely maybe the end of this year, maybe next year. We will see when we have the first data. Before the full system is commissioned, they will have data from a demonstrator that is also running at SNOWLab. I didn't mention this, but all this is installed in SNOWLab, that is an underground laboratory in Canada. Okay, similar to what we had in Gran Sasso, but the difference here is that it's not a tunnel that it goes through a mountain, but an active mining operation. So you go underground, so you cannot drive your car into the lab. It's a lot harder to get there, and it's a very harsh environment. We will talk a little bit more about SNOWLab, but it's absolutely an amazing facility where to run. And the shielding provided by the ground at SNOWLab, it's bigger than what you have in Gran Sasso, so even smaller flux from cosmics. These detectors do have timing capability similar to what we had with the liquid noble gases detectors, noble element detectors, so they can use active veto, and they do, okay, which is something that is very nice to have. So these here are the projections. I'm not going to go a lot in depth with this, but again, so look at the mass range for the candidates that they are targeting, and it's something slightly below 1 GeV to about 10 GeV. Here you have the other experiments with novel elements that take over, but in this range that is very close to where the shoulder of the neutrino fog is, okay? This is the region that they are targeting on. This is the beryllium solar neutrino flux, okay? So you can see different lines here. The different lines are coming from the different operation modes of the detectors. The high voltage go to lower masses, okay? Both silicon and germanium. Silicon goes slightly lower because it's a lighter nuclei, so it's, but this is, yeah, I'm gonna stop there. We can, so, and then you have these ICIP that are the ones that have nuclear recoil, electron recoil discrimination capability for germanium and silicon, okay? So this is the prospect for their sensitivity. And now let's go back to this excess, because what happens is that in the demonstrators, all the super CDMS sensors and I mean all the detectors that are cryogenic crystals do have this excess in low energy events. All of them, even if they are looking at light, ionization, or other stuff. And nobody claims that this is dark matter because the rates are vary widely, and they are not consistent. They have a time dependence that depends on things that you do outside. So this is not a dark matter signal. This is a problem or an issue with all the detectors. But it's very strange that many different technologies have the same effect, I mean, they see essentially the same thing, even if they are looking at different stuff and using different materials. So this here, again, just to give you an idea of how big this problem is within the community, is a slide from the IDM conference last week, okay, in which they dedicated a full plenary session to discussing this excess, okay? And this is just one slide summarizing essentially there are no clear ideas of what's going on there, but everybody is kind of getting together and trying to solve this problem or at least understand it. So some of the things that we discussed are included in this slide. The favorite explanation seems to be this, but nobody really knows, okay? And here I'm going to discuss some of the hints that are around. So these things here are, so this was taken from this paper that was also presented in IDM. This here is a small crystal with lots of TES on the top, okay? So this is one of the standard absorbers that we discussed so far. And well, they have to hold this thing somehow, okay? So what they did originally was to just have some glue to hold it into a copper mount there, a copper base, yeah? So, and what they see is that when they do that, and then they observe this, they observe some microfractures that are coming from mechanical stress. Very small, but still, we are looking at things that are milli-eV here. So very small effects can have a huge impact there. And then what they did was, instead of gluing this sensor to the copper base, they just place it there, no gluing, okay, and did the wire bonding, okay, so connecting these things to the readout electronics with these hair-like cables, and that was it. So it was hanging from the wire bonds. You can only do this with very small things, but it can give you a way of understanding what happens with something that is just suspended in hanging from these hairs, okay? And what they saw was this. So this, again, in the horizontal axis is energy and number of events, and the red histogram here is from the detector that was glued. And the blue histogram here is from the detector that was just hanging by these hairs, okay? And they do observe a big reduction. It doesn't go to zero, okay? So the problem is not solved, but there is a big reduction. How important or meaningful this signal is, it's not clear. So on one hand, we already knew that mechanical stress can produce these low energy events. And yeah, for sure, you are going to have more mechanical stress here because there is also a thermal expansion coefficients mismatch between silicon and copper. Both things expand and contract at very different rates when you change the temperature. So you would expect that there would be a pretty large stress here compared to something that is not glued. So how important this is, it's not clear, but it definitely gives you a hint or at least something to dig into and try to understand if you can reduce this stress by changing the way you treat these crystals. And that's the end. I don't know, there are 3 minutes. Do I have time to discuss something or if there are questions, we stop here, whatever. And maybe one of the questions will trigger what I want to talk about next.
Excuse me, you said that basically the detector was hanging by cables, right?
Yes.
And what if you use, I don't know, electromagnetic or disinterfering something?
Levitate these things?
Yeah, yeah.
I don't know. As far as I know, that has not been tried. most of these things are non-magnetic materials. So you would need still to add something that you can somehow control. But yeah, I mean, I don't know if that has been, I don't know that that has been ever tried, but maybe, yeah. At some point, if people get desperate enough, they will do it.
Okay, thank you.
Can you go back to the plot with the low energy excess in the crust experiment? The one that you said the signal would look like a WIMP?
Yes.
Yeah. I have two questions. First, what would we expect for just standard model particles in this plot?
So from just what?
Like, what would we expect for only standard model particles in this plot? And the other one, if they did studies with different WIMP masses or just half GV?
Oh, no, yeah. So they do studies for all the masses that you want to target, okay? So there are simulations and predictions. You have actually, in order to produce a limit or do a search, you really need to have an expectation for your signal. So there are, you can compute what is the expected signal for WIMPs for all the different masses and size, and strength of the cross section. Okay, so that's done. I'm just showing one because this is the one that best fits this particular histogram. But yes, there are. So that's regarding the signal. And what you expect from only standard model particles, it's harder to answer because the thing is, you can definitely have this result just from standard model particles if the background, if the radiation environment is selected so it does so. So it's not something unique from WIMPs and standard model particles. What you do is you build your shields, and ideally it's to build your shields so the backgrounds have a shape that is as different as possible from the signals that you have. And that's what we are doing when we are placing these things inside neutron betons and lead castles and things like that to reduce the amount of environmental radiation and just allow a fraction of that radiation to go in, and then we compute what's the shape of those backgrounds using Geant4 simulations or other means. And in principle, what they expect here essentially would be a flat background, okay? And that's not what they see. But in a way, we know that this is caused by standard model particles. So you definitely can have a way of producing these types of signals with standard models. I mean, one of the things that is really unfortunate regarding WIMPs is that the signal that you expect, essentially for the low masses, pretty much is just an exponential decay. And it's very, very simple to get an exponential decay from regular stuff. Okay, so if you are looking at other candidates at higher, that are not WIMPs, for example, if you are looking at dark photons, some of those actually predict a signal that is just a line at a particular energy. That is the mass of the dark photon. So that is very different from most of the environmental backgrounds that you are able to reach. But unfortunately, exponential decays are very common.
Okay, thank you.
Any other question? If not, I have one. What are the possible solutions?
Okay. So, there are many. People are trying a lot of stuff, but one that may be very nice, that it's a radical new direction, is this one. Is instead of using a crystal as an absorber, what you do is you use a superfluid medium, in this case helium. And the reason for using a superfluid liquid here, in particular helium, is twofold. Well, once you have a liquid, you cannot have stress. So there is no mechanical stress there. Then the other thing is that when a liquid is in a superfluid state, essentially what it means is that all the heat is shared equally among all the particles there, all the atoms there. And that translates into an extremely low rate of evaporation. So if you have any regular liquid not in a quantum entangled state, okay, even at very, very low temperatures, you will have some evaporation because the distribution of energy between the particles just follows ideally a Boltzmann distribution, and some of them will have enough energy because they will be in the tail to just fly away from your liquid. But in a superfluid medium, that doesn't happen. So all the things are bound together. You don't have any evaporation at all, guaranteed. Okay? So then, if anything evaporates from this, is because something from outside just kicked it. Okay? So that's what they are aiming for in this design. You have a superfluid liquid, then you have an interaction, and when that happens, you deposit some energy. Again, this energy will produce phonons now that they bounce in this volume, and at some point they are absorbed by one of these helium atoms, and that atom evaporates, just a single atom, okay, evaporates, and you hope to see it. Okay, so you place here one of these detectors that detect heat, okay, and this atom, when it evaporates, it will hit your detector here and then produce a measurable temperature change locally that you can measure. That's a big challenge. It has not been demonstrated yet, but a lot of people are working on this idea. And from the detector point of view, it is very nice, okay? But there are many, many challenges, of course, related to this. But maybe at the end, the solution, it's not coming from the crystals, maybe it's coming from liquids.
We thank Javier. And now we move to the question to the three speakers. So, who wants to start? Okay.
For Dario, how can you have phonons in a liquid medium?
So, I mean, it's the same. So, similar to what, I mean, the analogy with a string that you do like that, the string is fluid, okay? In the medium, you have, just vibrations from one atom that translates to another, and you can have modes. Everything is linked. It's not, the description is not the same as a crystal in which you have things that are very tightly bound, but it's similar. So it's an ordered medium, more like random position of atoms, but still you can have wave-like propagation of stuff there.
Okay.
Okay. Any other question? Well.
I have a super basic question. So what's the difference between the beam dump and fix at target?
I forgot. Yeah. Okay. So I think you can usually, I mean, there is no strict rule, but you can draw a line between a situation where you have your target, your beam impinging on your target, and the average number of interaction is lower than 1 inside the target, or is much larger than 1. So, for example, HPS, it has electron beam impinging on a thin target, and what happens many times is that the particle beam crosses the target without interacting, and that is a thin target. Otherwise, if you think of a beam dump, it's a thick target, and it always happens something. So it's really rare that an electron goes through, of 100 GeV goes through a few meters of aluminum. So I think that you can draw the line in that sense. Then you have also, obviously, mixed situation, because you can have multiple interaction in a spin target, or I mean, target that does not contain completely the beam, but still you have some shower initiation, so it is a bit of gray area, but usually we define the difference like that. So that's it.
Thanks.
Thank you. Questions?
I have just a question about this presentation. There was, during the scheme of one of the experiments, there was bias I plus and bias I minus.
Yes. This one?
Yes, yes. I just was wondering what is exactly bias I plus and I minus?
Oh, it's just that this one is connected to a voltage and this one is connected to another voltage, so a current flows through the tungsten link between them, okay, just as a resistor. And outside you measure the amount of current that is flowing, or the voltage drop in this resistor, just to estimate the resistivity, okay?
Okay, okay, thank you.
So I have a question about the last slide you showed, because the way you talked about these new detectors, new generation of detectors, I didn't feel very confident about we seeing one unity of helium atom and detect it. So how, you said it was very challenging to really detect, but how are we going to do this? It doesn't feel like we will have a great sensitivity with this kind of experiment. I don't know.
I mean, yes, I share your concerns, yes. The thing is that, I mean, we do have technologies in which we are able to see single quanta of stuff. For example, looking and seeing single photons, it's something that we do regularly. Looking at single electrons in even EV scale electrons is something that we also do regularly. This is something that has not been demonstrated yet, but it's not impossible in principle. I mean, it will depend on the amount of kinetic energy that this atom has when it leaves. So if you have something that it's living with, I don't know, MeV kinetic energy, then yes, it's super easy to see one single atom that has MeV energy, okay? But if we are aiming for something that is in the scale of EV kinetic energy in a full atom, then that will be a lot harder. But still, I mean, it's not impossible. The first, I mean, my impression is that the first iteration of these things, if they work, they will have a relatively high energy threshold. Okay, they will only be able to see atoms that come out from the liquid with a high kinetic energy. But at some point, well, if the idea doesn't, I mean, it may have other problems. So the thing is, at this point, it's just a concept. And there are demonstrations of some of the elements here. But it may be that when you put everything together, everything looks good, even if your energy threshold is high, and then you start putting a lot of effort in lowering the energy threshold. Or it may be that when you put everything together, you see something similar to this low energy excess or other problems with other experiences. Okay, now this is not the way. But at this point, we don't know. Yeah.
Good. More questions? Okay.
I have a question for the three lecturers, just out of curiosity. My impression so far from the lectures is that we have been mapping for WIMPs on many situations, and so far everything has not worked out. Do you think that when we finish this quest, will we find any evidence of WIMPs, or should we start shifting our search to other candidates? It's for the three of you. What do you think?
Okay, I can start, but
I can go first. I think that we already started shifting to other things, not necessarily shifting in the sense that we are stopping studying WIMPs, but we are just trying to see if there are other reasonable possibilities. At the same time, it's worth going on with WIMPs. So I think that at the end of the day, it's right to go in a different direction and to try to search for all the many possibilities that we have. If we have some reason to believe that one candidate or one theory is more motivated than other, it's reasonable that larger efforts are going to that direction. But still, I think in general, already there are several candidates from a really very low mass to WIMPs and over. So it's already happening, I think. I don't know what that's
I mean, yeah, definitely. We have to just find new places to look. So from the neutrino side of things, one thing that we can look for is like cosmic ray boosted dark matter. So if you look at like light WIMP particles, the problem with detecting them in your experiment is they just don't have enough momentum to give these nuclei or electrons enough of a kick to be able to see over your threshold. So one potential solution to that is assume that there is some ray flux of cosmic rays coming from like the galaxy center, which we know does exist, and say that those cosmic rays can give your WIMP flux between the galaxy center and your detector a little bit of momentum in the direction of your detector, enough to make those WIMPs have enough kinetic energy to make some signal over your threshold. And so that's a signal that we search for in neutrino experiments that can give you, hundreds of MeV of, say, electrons that would give you directional information, be able to point back to the galaxy center. And that would be another way to, with some model dependence, say that you could discover that sort of phenomenological dark matter candidate. So yeah, it's again just finding new ways, new places to look if we continue to not see the stereotypical WIMP.
yeah, I mean, I fully agree with what was said. So the community is already been shifting for some time already. My personal view for the WIMPs is that at some point it was the best candidate for many motivations. Most of those motivations are gone now for me. I think it's still a very viable candidate, and it's definitely worth exploring for sure. And we are doing that. But yeah, my view is that it's a better strategy now to just look everywhere, cast a wide net and try to look for other things. And that's what the community has been moving towards in the last few years. So in 10 years ago, it was all WIMPs, essentially. Since then to now, the light dark matter candidates have exploded, but also other options. So people are more open-minded about what it's meaningful to look for.
For Luca, you were mentioning in the first lectures that you were searching for displaced vertices. I don't know if you were searching for the same type of signal in this fixed experiment happening in CERN. That was just like a question because I was wondering, you're going to involve in your research maybe long-lived particles. So how, what's the lifetime you're expecting for them to have in this experiment?
Oh, well, it's really depending on the region of parameter space. So unfortunately, the lifetime of the particle, especially in the visible decay scenario, so where if you talk of a dark photon model, obviously, if you consider the visible scenario and you think how is the dependence of the lifetime on the parameters, it goes as a epsilon squared, and epsilon goes from 10 to the minus 2 and it's still reasonable to search up to 10 to the -9. So there are really many possibilities. There are regions that are accessible for search of displaced vertices on a fixed target, for example, like HPS does. And HPS has a sensitivity in terms of displaced vertex, which is of order of tens of millimeters. So we are expecting a particle produced with a GeV, order of magnitude energy, to travel of order of millimeters. But also you can have a very long-lived particle. For example, today when I talk about E137, they were searching essentially Alps actually, but they were reanalyzed in the context of dark photon, which travels for hundreds of meters. So very, very differently. And again, you arrive to the level that if you go down and down the parameter space, you have particles that travels for kilometers, so you probably will never be able to unless thinking of something very specific, to address the displaced vertex with a particle physics search.
So maybe for this concrete experiment regarding fixed targets happening in the CERN that you mentioned, would be like a few millimeters, maybe for it to not decay right after the detectors.
Well, basically you have to decide when you I don't know if I got correctly the question, but if you decide, when you think of an experiment, you decide which part of a parameter space you want to target, and when you build it by consequence of the properties of the particles, which are consistent with the parameter space. So, for example, HPS wanted to search in the thermal target, which was a JLab actually, and they thought of an experiment capable of detecting displaced vertex up to a few millimeters. So, if you want to explore or think it's reasonable to search for something else, you maybe will try something different. So, for example, bin dumps with a large decay volume, for example, like SHIP will be doing with this large decay tube to allow particles which are more long-lived than a few millimeters to decay. Also, you have to take into account the energy at which you are producing this particle, because the more energetic they are, the more they can travel. So there are many variables, and it really depends on. You have, first of all, you have to choose what kind of particles and what part of the parameter space you want to search for, and then you build your experiment. There are some regions that you cannot explore with a displaced vertex search because they decay promptly, and you have to be simply aware of that.
Okay, thank you.
Thanks. So I can take one more question if you want. No? Okay, so if not, we thanks again the three speakers. And now it's time for lunch. People that have to go to the USP, we meet outside. I see you tomorrow 5 minutes before 9, right?